How to Build an Aeroplane by Robert Petit. I translated from The French by T.O.B. Hubbard Ange. H. Lettiboer with 93 illustrations, New York D. Vanastrand Company, 23 Murray and 27 Warren Streets off. University of. Page 2. How to Build an Aeroplane. Page 4. Off. University of Preface books on the subject of aeronautics are numerous, but with few exceptions, they have neglected the technical aspects of the subject, and none as yet have dealt with actual aeroplane construction. The present work, however, treats this question full for the first time. M. Petit is an eminent French engineer who, during the past few years, has made a personal study of the methods of construction adopted by the great French firms. It is universally recognized that France, at the present time, has no rival in aeroplane building, and in this book the experience gained from close association with the best methods of what is now a large and flourishing industry is set out in simple language. Designers of British aeroplanes, it is true, will probably follow their own ideas in construction. But a great deal is to be gained from a general knowledge of the methods adopted by constructors in other countries, as the result of long experience and patient experiment. The following pages, from this standpoint, undoubtedly provide a full review of a department of engineering, whose growing importance it is difficult to overestimate. 206,432. Roman 6 preface. Already great strides have been made in the industry by British firms, and Great Britain is evidently about to regain her lost lead in aviation. It is hoped that this book may contribute in some small measure to the desired end. T.O.B. Hubbard J. H. Lettiboer. The translators desire to express their indebtedness to Mr. F. Handley. Page 4. The elucidation of several difficult points. There's introduction. ONL. Yesterday aviation was born. Today it is already called in Tobing Gavist representative industry whose future is definitely assured. 2 years shave passed since that great day when wested on the maneuvering ground of Issy-les Moulineaux, waiting anxious litoseth voice an aeroplane, piloted by Farman, Rice and Fly. All that have flights of previous day should made us confident, our expectation was not unmingled with quiet skepticism. For at his period, which has already passed into the realms of history, one could note implicitly rely on proper working of the motor, and severe criticism had been lenched against the design of the aeroplane itself. Farman flew a kilometer and returned to his starting point. Aviation had taken its first step. Aviation was established. Since then we have seen Blériot flying in his monoplane across the water from Calais to Dover. In the presence of this exploits, once that travel back with pleasure at the heroic age of aviation, Tothayars when a fusilitary madman, named Voisin, Blériot and Esnault Peltery, sought to free themselves from the fetters of gravity. In those days there was not a single manufacturer of aeroplanes, but those then sacrificed a dark corner off their workshops putting together, with the help of owner with their workmen, a flying machine off their own design, Havito de become aeroplanken. Roman 8, author's introduction instructors at head office workshops, turning out new machines every week, with whose performance note the technical reviews can keep pace. In this new industry, the same face are evident that characterized the history of the motor car. The pioneers of aviation have passed for good this stage the principally of the thing require demonstration. They are no confining their attention to the perfection of construction and to the lowering of prices. Many people, even the firmest adherents of the new locomotion, refuse to credit the actual existence of an aeronautical industry, believing rather that aeroplanes are only constructed torter in general engineering or motor works. They have in scout the idea of a spirit industry as visionary. Let those doubters pay a visit to the works of Voisin, Blériot, or Esnault Peltery, one and they will soon realize their mistake. The workshops resound with the murmur of incessant living activity. Lathes and machine tools, driven by powerful dynamos and motors, hum from morning to evening, splitting, sawing, cutting, shaping and fashioning the special varieties of rare wood brought over from America and Africa. Chips and shavings fly from the pine wood, and the raw material becomes smooth and polished, so that the air may slip easily around it. The workmen move hither and thither under the supervision of skilled engineers. In a corner of the works, near the tall double doors, a framework is attached there, flashing steel wires, aerodron tautby wire strainers, the motor with its rows off cylinders is built in, the sharp blades off the screw riveted, ready for cutting their way through fluid air. The aeroplane stands complete. One or Ledusad, Tothworks offer British constructors. Eds. There's introduction Roman 9 against that arc background of the workship it spreads, its broad wide wings, trembling, longing for flight and space. The doors opened, the straining machine emerges into the sunshine. The doors close again, in the spacelift vacant workman laying down thekeel of a fresh aeroplane. The industry of aviation is a living reality. In the belief that a description of the construction of an aeroplane its successive stages would prove interesting, we have sought in the following pages to present the knowledge and experience gained by many extensive visits to the various aeroplane works, in order that reader may have a complete grasp of the subject. It has been that advisable to give, in a preliminary chapter, some technical information regarding the theoretical calculations on which the design is founded, such as determination of the surface required, necessary horsepower, etc. On the fundamental technical principles will be touched upon in this part, so snatok see the limits of this work, which is primarily intended to present a general, and above all practical, account of the building of an aeroplane. Robert Petit, page 10. Contents page preface. V. Author's introduction. Roman 7 chapter I General Principles of Aeroplane Design Theory and Calculation I1. Resistance off, airtoa plane moving through it I2. Liftofa surface sod of velocity V meeting the air at an angle of incidence I4-3. Power required for sustentation. 6-4. Resistance to forward motion. 7-5. Effective unit power on the sustaining surface. 8-6. Superiority of aeroplane over every other type of flying machine in respect of lift. 8-7. Elementary calculations for design of an aeroplane fulfilling certain given conditions. 9-8. Application of motive power calculation of the propeller. 14-9. Arrangement of surfaces. 18-10. Lateral stability position of center of gravity 22-11. Longitudinal stability. 31-12. Variations in altitude. 35-13. Direction. 36. Roman 12 contents chapter Roman 2 page materials used in aeroplane construction. 37-1. General principles of construction. 37-2. Materials used in construction. 38-3. Fabric. 44 chapter Roman 3 The construction of propellers. 45-1. Preliminary remarks. 45-2. Procedure based on Mdr-Zwiecki's theory. 45-3. Other ways of designing propellers. The Colix and Tatton processes. 48-4. The manufacture of propellers. 50 chapter Roman 4 The arrangements for starting and landing. 58-1. General remarks. 58-2. Wheeled chassis. 58-3. Chassis with skids. 65-4. Combined chassis. 65 chapter V The fuselage building in the motor. The controls. 68-1. Necessary qualities of the fuselage. 68-2. Various types of fuselage their manufacture. 68-3. Building in the motor. 73-4. Arrangement of controls. 76. Contents Roman 13 chapter VI page The planes. 81. General remarks. 82. Biplane surfaces. 83. Monoplane surfaces. 83-4. The curvature of the cross-section of the wing surfaces. 86 chapter Roman 7 motors. 89-1. Fixed cylinder motors. 94-2. Rotary motors. 104 chapter Roman 8 The future. 112 appendix. The British green motor. 115. Page 14. Build an aeroplane chapter I General principles of aeroplane design theory and calculation. Every calculation relating to aeroplane design is based on the expression of the resistance offered by the airtoa surface moving through it under given conditions. For this reason, it is impossible to obtain rigorously accurate numerical results. The basis, the starting point, free calculation, is in fact a subject on which most eminent theorists divide opinions. Resistance of the airtoplane moving through it, the formula giving the resistance of the air cannot be stated in invariable terms eventode, and it is this fact which is the cause of so much hesitation on the part of the constructor in calculating the design of an aeroplane. The uncertainty of this formula should be ascribed to the presence of the famous or infamous coefficient k, which has formed the subject of so much controversy. The mysterious figure kashumes the most unexpected values, nor can thella waff its variations be determined. We cannot say whether this coefficient hides an unknown law, or whether it is a spirit value for each different machine. The solution of this problem has been attempted by many engineers, but hitherto without success. Only to how to build an aeroplane, recently Wright, an engineer well known for his work on turbines, has undertaken that off laying down a fresh set of values for aerodynamics, but his researches have not yet reached anything like finality. Two young engineers, Tariel, one published a treatise a short while ago, in which, by applying the principles of mechanics, they prove very clearly that the study of the motion of surface through here may be based on the conception that the press downward in a vertical direction a definite quantity of fluid. This interesting work cannot as yet be applied to practical purposes, but undoubtedly contains some excellent ideas. In any case, researches of this nature deserve very encouragement. We will, however, leave this controversy, and in our calculations we will take their assistance off the earth being proportional to the surface, and to the square of velocity of motion. These laws, which can be easily verified, have never been refuted, and will, in all probability, remain good. We will adopt the value of coefficient K0, 0.8 as determined by Eiffel as a result of high extensive experiments from the Eiffel Tower. This figure has usually given good results, relatively speaking, and seems to approach nearest to the truth. I can therefore adopt the following formula to express their assistance of airdo surface moving through it orthogonally, that is, perpendicularly to the direction of motion. RKSV20. 08 SV2, where cis the surface in square meters and v the velocity in meters per second. The power required to drive a surface in these conditions will, consequently, be equaling kilogram seconds to 0. 0.8 SV2, or expressed in horsepower, 0.08, VGP 75-1 etudes, Sir Lesherfiss's Port and Tesson Aeroplane. 1909. General principles of design 3. This formula shows us the limits within which we must avoid plane surfaces, perpendicular to the direction of movement, in an aeroplane. But formula, only applies to orthogonal motion, which has no interest for the study of sustentation. The only way to sustain a certain weight by means of carrying surfaces is to place a thelator in such a position that, ergivesipsum of its energy in the course of its flow past the surface. In the case considered above, the impact of the air on the planes the sole force that produces Budae's the surface is in motion, a certain quantity of air is thrown back in front. But, in order to produce continuous work, it is necessary for the air to flow away. It must be met at a forward edge of the surface, led to its rear, and inly abandoned when the whole, or the greater part, of its energy has been absorbed. It follows directly from this that the inclined position is the only one that can fulfill this condition. In the case of the inclined plane, the fluid must not collide with the surface so to lose its velocity, suddenly, and to assume a velocity in the opposite direction. On the contrary, it must preserve velocity in same direction as the relative velocity it possessed at first, and must only retain a sufficient part thereof, tonable it to leave the plane without interfering with the following masses of air. The inclined planes therefore re-employed in the aeroplane, hence it is essential to know the variation of lift as a function of the angle of incidence. Here again, opinions unfortunately differ. It is impossible to present numerical variations caused by decreasing or increasing the angle of incidence. The most we can say is that an increase in the angle brings about an increase of the resistance R. As in the previous case, therefore, we must employ such formulae as seem to approximate the most nearly to reality. Let ab fig. Be longitudinal section, off a surface, moving through here in the direction, off the rho at a velocity v. All that case can ever arise in practice. For how to build an aeroplane we will consider the air arriving beneath the surface and yielding its energy, due to the relative velocity v, in two parts. The first, R2, resisting forward motion, the second, RJ, producing sustentation. Of these two we needn't consider the latter, for since, in practice, the main object aimed at is to increase their resistance to forward motion, we may, in theory, consider it to have been attained, and fig. I assume that thesum total off the energy off the air is utilized for sustentation. In consequence, their salts weshall obtain air theoretical in the full meaning of the word, since they will finally give us the power necessary for sustentation alone. Roman 2. Lift a surface at a velocity v meeting the at an angle off incidence I by the lift of an aeroplane surface, a area s, meeting the aerotan angle with a velocity v, would note the vertical component of the resistance off the earth surface. In other words, the lift is the weight that can be lifted by the surface. If we take the velocity as unity, i.e. m per second, and if we give a surface an area, general principles off design 5 of I square meter, we shall obtain a lift in terms of unity. We can now work out our forces. Turning to the preceding figure denotes the angle off incidence. If a already been stated that we shall consider the as being pressed downwards. Since this air possesses, initially, relative velocity only in a horizontal direction, it will bits inertia resist this motion imparted toit and will produce a sustentation. Let us now consider a molecule off air at the moment off it striking thunder city off the surface at B. It will baimpellet in a vertical sense with a certain velocity v during gas pace off time that will depend on the actual width ACA boff the surface and will equal where it represents the horizontal projection off AB. The molecule forced downwards in this manner will resist this motion b developing a force proportional to its mass and ta the vertical velocity which it is given by the surface. Let's denote the velocity of the motion imparted to the air along BC. If this velocity were constant, the molecule off air would produce an offer energy after its contact at B, and we would have the case off an orthogonal translation of AB. But the air must flow from A to B. Consequently, the velocity must not disappear in spite of the amount of the energy thus given up to the surface. Totain this the air must possess, in addition to uniform vertical acceleration 7, which will give it a continuous value. In this way the molecule will exert against AB a vertical force in an upward direction, throughout that time that the surface and air attain similar relative positions. It follows that the most efficient surface will be so shaped that a molecule off air will continue to exert its force throughout the distance from A to B. We shall examine the necessary conditions to be fulfilled in this respect later on when considering curvature. The relative horizontal velocity off air being v. A. 6. How to build an aeroplane, mass off air m will meet the surface over ice cond. This is c mass m will be quantum, and consequent lithe lift off the surface will be expressed in the formula m. ACV, the German physicist Wegener von Dalwitz has deduced from this point a complete theory for the calculation of lift. After proving that the acceleration y is represented by 2 bc. V27c he obtains, by utilizing a formula analogous to that we have laid down above for fj the expression of lift is a function of the angle of incidence, 3 fs. 26. Cos 2 SV2. Although we should have liked to show the steps by which he obtains this result, lack of space only allows us to sectodern it a practical account. Let us take SAS being a square meter. The lift per square meter will be 4 F0, 26. Cos T, TGI, V2. Roman 3. Power acquired for sustentation. We have seen above the method of calculating lift off any given aeroplane surface when its area, its velocity off motion, and angle off incidence are known. For practical purposes, the most important consideration is the power required to maintain the velocity at the level necessary to fulfill the conditions of flight. In section Roman 2, we saw that lift is produced by the reaction of air which the surface tends to press downwards. The energy by which the nympaled will obviously be furnished. General principles of design 7 by the motor off the aeroplane. The expression will therefore denote the theoretical power required for the given sustentation, the latter being known a priori from the weight of the machine and its pilot. Every second a certain mass off air will therefore baimpeled towards the lower edge with an acceleration 7. If represents the difference in level between the forward and rear edges, it is evident that this mass off air, striking the surface at B, will gradually baimpeled downwards to A, that is, it is forced to descend at distance h with an acceleration 7. The energy required to produce this movement is m kilogrammeters. It must be remembered that the air possessed no vertical velocity before coming into contact with the surface. Their quisite power will 75 v 75 this gives us the power required to sustain the aeroplane. Whatever hypothesis we may have assumed at the outset offer calculations, it is obvious that the above result will attain our object. Our solution was to determine the conditions required for the aeroplane to leave the ground. I don't know the motive of power necessary to achieve this purpose. Practical considerations will allow us to amplify the figures obtained in the correct degree. Roman 4. Resistance to forward motion consideration off the power P provides the means to determine the theoretical resistance to forward motion off surface. It is evident fig. 2. That the power off propeller is utilized entirely in overcoming the component, not the resistance, R. We'll know the power from formula 4. Let us assume the efficiency off the propeller as 80. The actual power will be 0, 80p that is 0, 80 SV3, 6, 0, 26 cent, TGTTR. 8. How to build an aeroplane, the resistance to forward motion being N, the velocity off translation off the point O being V, we can write 0, 80p 0, 80p and V. Hence N with the help of this formula we shall later be able to estimate their resistance to forward motion off any aeroplane FIG. 2. From the velocity obtained during flight and from the power developed by its motor. V. Effect off unit power on the sustaining surface on the other hand, knowing from formula 3. The lift off a surface moving at a velocity vatten angle off incidence, and, on the other hand, knowing the power necessary for sustentation, we can determine the work done by IP by dividing lift by the power. 7. FO. 26 cos 2 SV2. 75 F 0. 26 sin. TGISV3 VTGI VI. Superiority. Off the aeroplane over every other type of flying machine in respect off lift. In the foregoing calculations, we have always considered the downward impulse imparted to certain mass off air. All principles off design for which a certain power was required. We have further seen that the work Tobadone was greatly inferior to the force of gravity. Practice confirms the conclusion. To take an instance, Santos Dumont's aeroplane, weighing, including the pilot, 150 kilograms, 330 ibs, rose from the ground when the screw propeller gave a pull of 60 kilos, 132 ibs. Again, the Wright biplane sustains 500 kilos, 100 ibs, while the thrust off the screw is about 103 kilograms, or 51. 5 kilos, 113 ibs, by each screw. But if we turn a tow helicopter or flapping wing machine, we see immediately that the propelling organs must produce a first fall of vertical force, neutralizing that of gravity, and this without reconing the power lost in consequence of the extrema fluidity of air. The aeroplane therefore provides the only economical solution to the problem of mechanical flight, nor can machines of a different type that may be utilized in future ever deprive it of this advantage. Roman 7. Elementary calculations for the design of an aeroplane, fulfilling certain given conditions, when o possess a knowledge o free element entering into the calculation of the general features of an aeroplane. In practice, constructional requirements will enter into this calculations, butanly in suffer as the strength of materials is affected by the factor of safety and the modulus of the metals used. Example will demonstrate more clearly than any amount of explanations the exact method of procedure in designing an aeroplane. The problem may be approached in different ways. It may be necessary to calculate the sustaining surface from the given horsepower of a motor, which is available, and which one wishes to employ. Or the requirement may be that a surface off a given area should carry ascertain number of passengers, in which case we should first know how to build an aeroplane to calculate the speed required, and thence deduce the necessary power. A sage general rule, the only conditions imposed to effectuate off the aeroplane and the speed that can be attained without danger according to the dimensions off the maneuvering ground. Nowadays, speed at which an aeroplane should leave the ground is usually taken as between 60 and 90 km per hour, that is, between 16 and 25 meters per second. The starting grounds utilized, such as Issy, Chalons, Buck, Juvisy, etc., render higher speeds dangerous. One before we can increase the figures given above, we should beable ta foresee with absolute accuracy at which precise spot the aeroplane would leave the ground, which isn't yet the case. The piloting fan aeroplane subject ta so much uncertain to that the minimum velocity forecasted is sometimes attained only after considerable delay, and it is evident that in these circumstances relatively restricted starting ground would giveristo zero stangers. The weight off the aeroplane sewn off the factors known by the builder a priori has starts, in fact, with the knowledge off the number off passenger shoeishes ta carry, off the approximate weight of motor, framework, etc. Having made the preliminary remarks, we can now set ourselves the following problem, which will serve as exempli off the method of applying the formula given above. An aeroplane designed to carry popple wasin all 500 kilos, EU IBS. The starting ground limits the speed to 60 km, ph. What are the characteristic features off the aeroplane? Our solution will be divided into several parts. Surface themians off construction at our disposal today do not admit off a greater load than 15 kilos, 33 IBS. Per square one the same uplistuer English ground such as Blackpool, Brooklands, Shell Beach, Barking, etc. Eds, general principles off design and meter, but within these limits we can depend on obtaining large margin off safety. The carrying surface will therefore be 33 square meters. This figure, however, isn't final, since it will have tobe slightly increased afterwards to compensate any variations due to the designed angle of incidence and tonide departure, adopted to increase stability from the normal position off planes, as in the case where the airplane at a dihedral angle. In other cases, viewing tips of an aeroplane, seen from the front, turn it up, in imitation off the curved extremities off a bird swing. One, the efficient surface in such a case no longer coincides with the actual surface, but a horizontal projection off the latter, which varies with the cosine off the above angles. But these observations need not be taken into consideration until we proceed to the arrangement for carrying surfaces according to the special methods adopted by different constructors. 2. Power their aeromoney ways of calculating the power needed to raise from the ground an aeroplane whose weight, surface, and speed are known. Every method is to certain extent based on practical experience, and its accuracy remains more or less open taught out. The laws of aerodynamics are not precise, enough as yet followed without discussion. The calculation off the power off an aeroplane motor is usually unreliable, and the figures arrived at for a given machine, which has not at the time been built, often shown to be insufficient when it comes to practicaltist. But this does not apply to well-tried type of machine. All Blériot machines, for instance, possess a certain similarity of character, which makes it possible to apply the observations made on an ion off 1M. Tatton's Aeroplane an instance. 12. How to build an aeroplane them, to every on off the remaining machines off the type. Unfortunate lithelamites off this work, Donatello, Usto explains some off the theoretical methods employed. We will therefore confine ourselves to jiving some figures obtained from certain existing types of aeroplanes, and jiving an approximate estimate off the power they require. Aeroplane, general principles, off design 13 when proceed as follows. In the formula jiving the lift, we make S and VI. There remains F0, 26 cosi, TGI. If no we work out every value of F for every value of from Edo 70, we shall know what angle of incidence must beat up TED for a surface of ISK, M, moving got a velocity off M, PS, tall if chosen weight off 15 kg. But in order that the machine may leave the ground we must have VF, or 1516, 62F, hence F0, 054545. From the table off we'll use we have just previously calculated, we find that 26 is the value of corresponding to 054545. According to formula, 7 PV 75 analog of F will give us the value of F. But Asarul, according to Wegner van Dalwitz himself, it is more convenient in regard to F and to the corresponding angles to calculate the value of FP te IP75 obtained by making V and FF synth the formula which gives P. Wethesgetno, the power needed per unit off speed. The total power pis consequently obtained by multiplying P by SV3, in our case P0, 000317, hence PSV8 PIP, whence P33I6, 630. UO3I7P47LP. The power required to raise our aeroplane from the ground therefore works out at 47 IP. A 50 HP motor. 14. How to build an aeroplane will amply suffice, since the method of calculation followed allows for the simultaneous variation of the angle of incidence and the speed without affecting the result. In practice, as is almost invariably the case, the angle of incidence will probably be smaller and the speed greater. To sum up, the chief features of our machine are weight, 500 kg, I 100 IBs, carrying surfaces, 33 SQ-M motor, 50 IP, probable speed, 70 kph, load per sq, M 15 kg, 33 IBs, Roman 8. Application of the motive power calculation of the propeller turn to practical use at the power of our 50 IP motor. The power developed must be transformed into tractive effort acting on the surfaces, compelling the latter to move forwards, this forward motion resulting in sustentation. These transformers will have to find their point of support on the air, a fluid and unstable medium. The inlaid vis employed in aeronautics to fulfill this purpose is the screw propeller, which consists of surfaces or in a special manner about an axis to which the air affixed. The rotation of the axis causes the surfaces to rotate likewise and to drive back the air to the rear, thus tending to move forwards. This tendency to advance is utilized to drive the aeroplane. It follows that the design of an efficient propeller is a matter of extreme delicacy. The whole question of propellers is very little understood at present day, and it is difficult to find a complete theory for their calculation. Many theorists have examined textion, but among them only very few indeed have evolved a comprehensive and connected theory. Among the remainder there are some Sir Hiram Maxim and William Froude, for instance, who have emitted correct views and made valuable general principles of design 15 tions, but without explaining them with sufficient clearness. Practical experiment still remains master of the situation, and the majority of constructors follow their own special method of design. But, as a rule, their chief error lies in fixing a priori the diameter of the propeller. Nothing could well be more illogical. The diameter, the principal dimension of the propeller, is the first that to vary according to the power. Their next mistake, usually, is to base the other dimensions of the propeller on the of its diameter. One builder, for instance, favors a pitch IJ diameters, the width of the blades being made diameter. These methods, to say the least, lack the mathematical accuracy the taught first consideration in propeller design, and low efficiency can usually be ascribed to these causes. The most complete theory of the screw propeller in existence is the unpublished last year by the Russian engineer M. Dr. Zhuiki, whose remarkable works on fluids are widely known. One Dr. Zhuiki's theory is worth following, principally an account of strict reasoning in which it is founded. Moreover, even if it should prove not absolutely accurate, it is the further advantage of result in Gina method of construction, which can be immediately applied in practice. Further reference to this point will be made in the chapter on the construction of propellers. Consequently, in his case, errors which cannot be eliminated from a theory are, at any rate, note increased faults in the construction. We will, therefore, in the next paragraph follow Dr. Zhuiki's method of calculating the design of a propeller driven by a 50 IP motor, revolving at 600 RPM or 10 RPS. Number of blades on this point Dr. Zhuiki's theory is no explicit enough. In consequence, we will adopt the usual number of blades too, without going into the one Dr. Zhuiki, Des Helices Arians, 1909. Steen How to Build an Aeroplane Theoretical Question. At his time, we may point out that 3 blades might be preferable. Diameter of propeller torriv at head diameter we must first calculate the modulus of the propeller, V16M, that is M0. 26. 27 TZ 27 TIO the diameter given by DMZIC2, 60 meters. In reality, the width of the blade is constant. This is what M. Dr. Zhuiki implies by the term specific width of the blade. It is constant, and as can be shown mathematically, equal to the modulus. WO 75 MO, 75x0, 26.0, 195 meters. From the working drawings given in M. Dr. Zhuiki's book we cannot construct the templates for the surface of the blades, but this will be dealt with in the chapter on construction. The propeller off or aeroplane will, therefore, have the following dimensions: diameter 2, 60 m, specific width 0, 195 m, RPS 10. The blade sought not, as is sometimes thought, to start from the boss, but at a certain distance from it, equal to half the modulus m, or in this case 0. 13 meters. Monothatany point on the propeller diameter revolves at a speed inversely proportional to its distance from the center. The tips off the blades move at a velocimeter y, n being the number off rev, p sec, and d the diameter. Consequently, as we approach nearer to the center, the speed will diminish in the proportion given, and the angle of incidence off the blades must be increased to produce the same amount off work. But the one modulus is that mused bm. Drs uike toad note, the pitch constant, general principles, oft assign 17 effect, off this increased angle off incidence at appears after, ithis reached a certain point. In a communication ta the Academy of Sciences in Paris, the late Captain Ferber lay down the following axiom which bears on the point, but isonly off importance in actual practice. Rogt JL, Fig. 3. Whether a plane move as through here in an inclined position or almost at a tangent trajectory, their distance off the earth a gravitating tendency off, total weight remains almost the same. Whether f4 reach a point at which it is preferable to cute away the blade, a fact which, as we have seen, is in accord both with theory and with practice. Fig. 3 gives a diagrammatic view off the propeller and its dimensions. 18. How to build an aeroplane, having explained the method of calculating the principal dimensions off the aeroplane and propeller, every one of these calculations being based on theoretical principles we cannot turn to their practical application. For a special C, it is not sufficient to give the carrying surfaces a certain area. There should pace a matter of equal importance. The efficiency of the carrying surfaces, in fact, varies greatly with their shape, and above all with the form of the perimeter. Roman 9. Arrangement of the surfaces. One fact this being noticed during the course of free experiment dealing with resistance off the earth passage through it off a plane surface, i.e., that if the resistance R is proportional to the area of the planet varies with their perimeter. It has always been a point of capital importance for the development of the aeroplanedo, determine the causes of these variations. The first definite results were obtained by Ladantek. Experimented with planes which were suitably ballasted and caused to slide down a wire at a speed of imi per sec. The area of the planes was exactly isk. M, the coefficient quas in this case, therefore, equal to the resistance. It was proved that value of K varied with the shape of the planes. Thus the resistance to triangular shape is greater than to square off the sama area, while a circular plane experiences less resistance than the square one. The resistance was therefore proved to increase with the perimeter of the surface, independently of all other factors. M. Canovdi has made similar researches and has given the following table. Shape, general principles, off design 19. This table already shows the influence of the position of the greater city of rectangle relatively to the direction of motion. M. Eiffel has obtained the following values. Shape, 20. How to build an aeroplane to consult on this point. And off these, Lilienthal Istobe preferred to the others reason off the curate measurements he gives, and to which he'll ways attach the greatest importance. We will therefore turn to his book 1 for a model on which to base the shape of surfaces off our monoplane. It may incidentally be pointed out that the majority of existing monoplanes indirectly proceed from the same ideas. The Blériot, Esnault Peltery, and Toynet Machines FIG. 4. And others have surfaces shaped on the lines followed by nature in designing Gabbard swing. Let us take the wing of Fastork. Lilienthal Gaveset following dimensions, Fig. 4. It should be noted that the tips off the primary feathers are not included in the total length. The entire span off a stork swingsis therefore equal to 6 times their width. But these dimensions cannot be followed with absolute fidelity, since the stork belongs to the class of sailing birds, who swing relatively longer at the base than those one der Vogelflugels Grundlage, der Fliegkunst. General principles oft assign 21 off the soaring birds, as is shown perfectly clearly in Mouillat's Empired P-Air. In the wings off an aeroplane, therefore, the maximum width it not to be less than thof the total span. This proportion is the adopted by M. Tatton in his Aeroplane, which has a ratio of 5 toy. It must, however, be acknowledged that in arriving at his dimensions, constructional requirements of FIG 5 been taken into consideration, for an aeroplane must not be given too large span, since this would necessitate the construction of immense broad sheds and would seriously affect the solidity of construction of machine. In preserving the area off the surfaces, it becomes in consequence necessary to increase the width relatively. In accordance with the above remarks, when I proceed to range at the carrying surface, offer projected aeroplane according to Fig. 5. The span of 13 meters will not appear. 22. How to build an aeroplane too great if it is remembered that the aeroplane is to lift 500 to 570 kilos, 100 to 1,250 ibs. The Wright machine, which lifted a similar weight, has approximately the same dimensions for each of its planes. The length, fore and aft, off the machine will be roughly equal to the span. Here again, where a guided by nature and be existing machines, it is clear that where stability is obtained by means of a tail, the greater the distance of the latter from the carrying surface, the greater will Bates' effect on the longitudinal balance, on account of its leverage. But since an increase in this distance entails difficulties of construction and makes the machine unwieldy, the length is not allowed to exceed the dimension of the span. This arrangement is therefore advantageous that tailplane acts in the same part of the machine itself, so that the danger of currents of different directions acting on different parts of the machine is decreased. X. Lateral stability position of the century of gravity before adopting any specific means for ensuring lateral stability of any ability. The latter must be considered in every position it may be caused to assume during flight, and in each case the sum total of the forces acting upon it must be taken into account. In this way, the aeroplane is considered first during normal flight, i.e., when it strays toreless in a straight line, and later in any departures from the normal, such as swinturning, before adopting a particular method of preserving the stability of any ability during its flight in a straight line. It will therefore be necessary to use the method is sufficient when the forces acting during gathering are taken into consideration. Before we proceed to examine the effect of the center of gravity, it is necessary to state that we need only consider the resultant of the forces and its effect, and that no attention must be paid to them as leading effect of individual components. General principles of design 23A. Flight in a horizontal straight line, in this case the aeroplane is only subjected to force as weight and lift. Under their combined action, the aeroplane is in equilibrium in calm air. The ligature inherent in design, which will avoid sitting off the aeroplane if it is struck by a current of air, is to place at the center of gravity below the center of resistance. This is an essential FIG. 6. Condition of lateral stability in any ability. When the weight is thus disposed, as soon as the aeroplane tilts to one side, the component GJP, through its lever arm OG, tends to restore the aeroplane at position of equilibrium. This lever arm is in any case constant, but since GJP increases with the tilt, the action of the weight will increase in like degree, with excellent results. This application of the center of gravity is shown in elementary physics by the pendulum. In proportion as the center of gravity is situated closer to O, the sensitiveness of the pendulum. 24. How to build an aeroplane increases. That is, its tendency towards equilibrium grossless. At a hedral angle off the plane's eye. Each wing being turned upwards laterally brings about great stability, but this method also is only effective when the center of gravity is low. Since it is that disadvantage of entailing an increase in the sustaining surface, and of behaving very badly in side winds, it is preferable to employ wings with FIG. 7. A continuous forward edge mounted above the plane containing the motor. The monoplane Blériot Roman 12. Fig. 7 is excellently designed in this respect, and has proved correctness of the system of construction in practice. B. Turning some few constructors, such as Esnault Pelterie in France and Grade in Germany, have, on the contrary, placed their center of gravity above the center of resistance, with the objective rendering turning movements more easy to execute. Let us see what will happen during that turning movement of an aeroplane with the center of gravity situated at different points. Let us take an aeroplane, Fig. 8, whose center off gravity. General principles, oft assign 25 is situated at G, and which Isterningen the direction of Thero. Let Bitha radius off the curve described around the center O, Themas off the Aeroplane. During its rotation round the center off the curve, the Aeroplane will be subjected to new force, which will tend to drive O. Fig. 8. It away from the centrifugal force. This latter force must be reckoned with, and I squalto it will therefore tend to force the Aeroplane at a theater city off the curve. 3 different cases may arise according to the position off the center of gravity relative alito the planes AB. I. The century off gravity is enable with the plane let a be Bethy Aeroplane Fig. 9 seen from the front, turning ground O, in a direction towards their radar. Owing toits. 26 How to build an aeroplane rotation round O. The aeroplane will be forced towards the MV2 outside by reason off the force applied to the center P of gravity G. It is manifest that if the plane remains FIG. 9. Horizontal. The aeroplane will be diverted from its course, MV2, since on the side B will oppose the force. In order to neutralize this force, it becomes necessary to resort to FIG. 10. Another method, which consists in tilting the aeroplane laterally, as in Fig. 10, so as to create an antagonistic force. Since their distance R remains perpendicular to AB, it will be tilted with the plane. It can then be resolved in Totwa forces, G mand Gn, the former vertical, the general principles, oft assign 27 latter horizontal. Thingley will be regulate either automatically or until Gn Gf. This action may be obtained by many different methods, every one of which, however, really amounts to warping off the surfaces. The aileron, one being lowered, the air is confined in a pocket and tends to raise G around thesis G, whilst the aileron 2s raised, 8 to descend. It will be noticed that in this first case, in which the center off gravity is situated onalval with the planes, the weight thus no effect on the evolution, since only acts as the center off rotation. The force Gn, which is equal and directly opposed to centrifugal force, will simply neutralize the latter without exerting any other effect on the aeroplane. For the simple reason that in this case there exists no verarmallowing the forces that are called into playdupsa transverse equilibrium, the tilting off the aeroplane, and consequent lithotoff the resistance, haste the inevitable result of decreasing the lift, which before the turning movement began was equal to R, but during the turn isonly equal to R cos A. The aeroplane, therefore, will descend during the turn. And this actually occurs, so that the pilot must, before tilting his aeroplane for the turn, ascertain that his height above the ground is sufficient to allow him to clear any obstacles during turning. The decrease in lift brings about a difference between their resultant off the forces acting on the planes and off those acting on the center of gravity. The latter is slightly stronger than the former, and force F forms with the force ran angle, which is very small, but nevertheless appreciable. The result is a component which, in case the aeroplane is tilted too far, will cause it adrift to thinner city off the curve. But if, on the other hand, the aeroplane is not tilted at a sufficient angle, the force resulting from G and F will 1. Move able wingtip or auxiliary plane. 28. How to build an aeroplane be superior to E, and the aeroplane will be diverted to the city off the curve. It will be noticed that fall in the path of flight off an aeroplane during turning cannot be voided by varying the speed, since if the latter is increased so to increase OM, their salt is to amplify in proportion the centrifugal force, and consequently, the tilt off the aeroplane required to overcome it. It must not be forgotten that the resistance off air and centrifugal force are both proportional to the square of the linear velocity. 2. The century off gravity is situated below the planes in this cassette effect, off the weight packs detrimentally during gathering movement. We have seen that the essential condition preventing the aeroplane from being diverted from its course was to tilt it towards the center off the curve. This tilt can be regulated by the pilot, let us examine thection off the weight P during this maneuver in the present case. Rigidity of construction, as in Blériot Roman 12. Prevents any alteration off the relative positions of Thetwo straight lines a band OG. Let us consider the aeroplane when tilted at an angle of forturning, Fig. 11. Since the planes are rigidly connected to OG, which remains perpendicular to them, They will cause the latter to assume the same angle of inclination. The center of gravity will be displaced to GJ, where thuate packs. If we take thesum off, forces acting in O, we obtain the product F. At Jeet we have a force GE, forming with F an angle ponthicide towards P. We have auradison that the tilt off planes causes the lift and weight come unequal. The force G, and the angle P produce C component GD, which, acting at the extremity off the lever OG1, tends to restore the aeroplane at a horizontal position. If the center, off gravitalis below the planesit thera 4 hinder sterning movements to certain extent. Every general principles, off design 29 body who witnessed theft flights during the Rhymes meeting last summer, must remember the tendency off the aeroplane Bleriot Roman 12. Toba diverted from its course when attempting to turn. It is therefore evident that the first effect ophalo position off the center, off gravity is good, but that as soon FIG. Roman 2. As thighs effect becomes appreciable, the force GJD appears and neutralizes it. On the whole, then, a low center off gravity is bad for turning movements, but that turning movementally forms a small incident in flight. Too great attention should not, therefore, be paid toits alongas the velocity, off light off an aeroplane remains what it is today. Flight in a straight line must be chiefly considered, and this favors the position we have just discussed. What is the best way to obtain a low center of gravity? Off the University of How to Build an Aeroplane, the oldest method was to arrange a plane as that the formed an obtuse or dihedral angle. Unfortunate his method is bad, for the reason that it renders the aeroplane more likely to capsize in a side wind. In our opinion, it is greatly preferable to build the plane's own continuous surface above the frame containing motor, tanks, and pilot, after the method adopted by Bleriot in his monoplane No. Roman 12, which could fire and was destroyed at Rhymes on August 29, 1909. 3. Century of gravity above the planes. This is the position adopted by Esnault Peltery in France for his monoplanes, and in German biplanes of grade. Referring topic. 12. It will be seen that, for the same reasons stated in the preceding section, the inequality between the lift during a turning movement and the weight tends to accentuate the inward tilt off the aeroplane, thus preventing its diversion from its course. This position off the center, off gravity is therefore excellent for a turning movement, which be it can accomplish at a high rate of speed, but for maintaining stability during straight flight it is most deficient. Any departure from equilibrium is immediately increased by the high position off the center of gravity, and itis exceedingly difficult to check this tendency set. The dangers of the system have been practically illustrated by the accidents that have occurred to the Esnault Peltery monoplane at Buck. 1. On the whole, the problem of the stability aeroplane may be said to be in complete accord with the laws of the pendulum. The 3 cases we have considered follow the laws exactly. From this we may conclude that the best method for ensuring stability is, at narrate at the present day, topless at the center, off gravity below the planes. 1. On more than any occasion the machine turned turtle. Eds, general principles, off design 31 as soon as the speed of the aeroplane reaches a sufficiently high figure, stability during straight flight will no longer need to be considered. Then, we shall only have to concern ourselves with stability during turning movements, and not till then will the principle adopted by Esnault Peltery prove practicable. For its high speed will render the aeroplane indifferent to any atmospheric currents, thus ensuring stability during straight flight, and the center of gravity, then situated above the planes, will allow it to execute the sharpest in safety. But at present time when the speed of flight is relatively slow, whether an adapt the system, but must rather concern ourselves mainly with the stability of aeroplane during its flight in a straight line. The center of gravity, therefore, must be placed below the planes. The future will see its position altered to above the planes, thus vindicating M. Esnault Peltery's contention. Roman 11. Longitudinal stability. The longitudinal stability of an aeroplane offers few difficulties. It is automatic, provided always that the 32 How to Build an Aeroplane. General principles off design 33 surface off the elevator be sufficiently great. 2 distinct systems of obtaining stability may be employed. In the first, the horizontal rudder is placed in the rear. In second, it is in front off the carrying planes. To the former type belong the voice in machines, Ta the latter the Wright Aeroplane. The majority of machines today, a Samatter off act, belong to the former type. The second is mainly favored by the American school, the Wrights, Herring, Curtis, etc. Figs 13 and 14. We will now consider thection off the horizontal rudder in these machines during ascent and descent. Let us take the aeroplane with a carrying plane AB, Fig. 15. Moving in the direction off the row out of velocity V. The air exerts a vertical resistance F applied to the point M. Let use assume that the center of gravitalis at the point gone the vertical line A. Thu 8 pof the aeroplane. Equal bu deposited a thelift, acts on this point. Acapel will therefore air standing tottern the whole off the plane a around a horizontal axis passing through the point cat the center off the line joining the points, where thetwo forces area played. The surface a B will assume the position A tick B, and this must be voided. In order to counteract this couple, a surface CD is placed in their air off AB. The surface C receives from the air a vertical force, F which counteracts the effect off the couple 3 FIG. 14. How to build an aeroplane owing to its liver arm O. In order to overcome the couple we can also, within limits, bring the vertical line and nearer to the point M. From the foregoing argument it is evident that if center off gravitalis to the off the center off pressure, the surfaces which produce longitudinal stability must be placed behind the main planes, but that they must be situated in front whenever the weight is applied forward FIG. 15. Off the center off pressure. For this reason, the stability surfaces are situated aft in the voice in aeroplane, in which the motor and pilot are placed near the edge off carrying planes, whereas in the right machine, in which the passengers are situated near the forward edge off planesi. E. In front off the center off pressure the stability surfaces are placed in front. Figs. 15 and 16 show the distribution off forces in Voisin and Wright aeroplanes respectively. General principles, off to sign 35 Roman 12. Variations in altitude the aeroplanes caused torice or descend beam thods, which differ according to the various builders. The majority utilize, for this purpose, the stabilizing surfaces off the aeroplane, irrespective of their position, by racing its singly off incidencia, and consequently the force F. The foregoing diagrams clearly show that in this casathingly off incidence, off the main carrying planes will beltered, thus causing the machine to move in an FIG. 16. Ascending or descending direction. Another class of constructors, among them the Voisins, use a horizontal rudder situated in front, independently off the stabilizing surfaces. Thection off the elevator isoscelically understood. If we increase its singly off incidence, it will obtain greater lift, thus increasing the incidence off the main planes in like measure. Its action is therefore the same for ascending or descending gas in maintaining stability. The aeroplane off the Brothers Wright possesses the great advantage of enabling the machine to ascend or descend very rapidly. The position of the elevator in front renders it very powerful and consequently rapid in its action. And this, 36 how to build an aeroplane unquestionably forms one of the best features of this machine. Among those who have adopted the Sama system are Blériot, Esnault Peltery, Tatton, Santos Dumont, Antoinette, Piscoff Coachland, etc. The number of builders who have adopted a joint elevator and stabilizing surface is small, and includes Voisin, Bonnet Labranche, and Farman. Roman 13. Direction it would be necessary to devote an entire section to textion off direction, since it possesses little special interest. The solution simply consists in utilizing vertical planes turning round a vertical axis. This concludes our study of first principles and general technique of aeroplane construction. Perhaps briefness offers summary of the calculations and method of designing an aeroplane demands an apology. Within the limits of the present work it was, however, impossible to enter into lengthy technical discussions. The effect of the curvature of the surfaces will be dealt with when the construction of the framework of planes is considered. Further, in the chapter on the construction of propellers will be found a review of general methods hitherto adopted. Chapter Roman 2 materials used in aeroplane construction I. General principles of construction B. Eries and of its being required to fulfill so many conditions simultaneously. Aerial construction, ISON, of the most difficult tasks, to which man has for Sethishand. The apparent contradictions which constantly occur make it a fecund source for researches for the engineer, who is a specialist in the strength of materials, while the metallurgist will find an occupation in the search for suitable metals. The skilled mechanic will evolve his own special structural designs. Briefly, almost every branch of industry is called up and to perform its separate part in aerial construction. The first essential requirement of a flying machine is that it should be strong. The second, that it should be light. In addition, the structure must have enough rigidity to prevent it from being deformed in flight by the normal action of the air. It should, however, be rigid only as a whole. That is to say, if, instead of being supported by the uniform action of the air on every part of carrying surface, the machine were, so to speak, suspended from one single point, this point must possess some freedom of movement. Flexibility, therefore, is another essential feature of construction, butanly within definite limits. Tombody althus equalitas in a single structure is addis of manifest difficulty, and requires first-class materials of construction, which must present a maximum of resistance to every kind of stress and strain. 38. How to build an aeroplane. Roman 2. Materials used in construction. Metals contrary to expectation. The advent of aerial locomotion has not brought about an aluminiumage. Notwithstanding its extreme lightness, this metal does not, as a matter of fact, possess sufficient strength, whatever its method of utilization. It cannot be used in the form of wires. Its tensile strength never exceeds 25 kilograms per square millimeter. Its bending strength is even worse. It is not very cohesive, a fault which is aggravated by vibration. It can only be used for parts which are constantly subjected to compression, as for instance in the sockets for uprights in the voice in biplanes. The motor industry is gradually banning aluminium, and the day is near when not a particle will be included in an aeroplane. Steel becomes more important every day. It is without question the best metal available at present time. Weight for weight, its strength is much greater than that of aluminium. Moreover, it is one of those rare metals that work as well under tension as when subjected to bending gravitational strain. The development of the steel industry is of comparatively recent date. For long the speed of machinery was not designed to exceed some 50 revolutions per minute. The construction of hydraulic turbines followed by that of the explosion motor, and lastly, by the steam turbine, created a demand for a metal capable of withstanding enormous velocities of rotation. Then arose, by the side of the great metal industry, that of special steel. The latter attracted a large number of distinguished metallurgists who have succeeded in producing steel alloys of extreme strength. The famous Krupp works in Germany produce nickel steel which, in the form of wires, can withstand a strain of 165 kilos, 364 ibs. Persk. A fact. Materials for construction 39 which shows that steel, with a specific gravitable that of aluminium, has a tensile strength 6 or 7 times greater. The proportion of carbon in steel is an important factor of strength. Hardened steel is much stronger than ordinary steel. Thus, the nickel steel referred to before being hardened only withstands a strain of 84 kilos 177 ibs. Persk. Many varieties of steel may be employed in aerial construction. Their quality varies according to the proportion of other metals contained in the alloy, such as nickel, chromium, vanadium, silicium, etc. Steel is chiefly used in the form of wires in the building of an aeroplane, for the latter contains no metallic portions, save, of course, the motor chassis and occasionally the framework. The following table gives us breaking strains of different wire shaving gasction of isk. Iron wire drawn, 5,670 kg, 123,150 ibs, tempered, 4088 Hopper metal, 140,310 delta, 98,216 Bessemer steel drawn, 65, 143 tempered 40-6088-132 zinc, 1942 lead, 2, 24, 8 silicium bronze, 65-85, 143,187 aluminium, 23-27, 5,060 copper 4088 Thebo figures show that silicium bronze is fairly solid. There would be no advantage, in point of weight, in employing this metal were it not that it possesses own most valuable quality, It can better net perfectly, and with a steel screw tap, gives very smooth threads in which the screw hasna play. In addition, the threads will be found as solid as possible, having regard to their section. This bronze is therefore used in the manufacture of how to build an aeroplane wire strainers, which must be able to stand the same strains as the wire to keep taut, otherwise the strength of the latter would be useless. A wire strainer simply consists of a bronze screw nut with twa threads, one at either end. In toe hitch enter two screws provided with eyelets. Toe hitch area attach the ends of the wire tobe stretched. The wire is strained by means of a gudgeon ninth nut. There are, of course, a good many types of strainers. Their only point of difference is in them and are off threading. Figs 17 and 18 show two different types of strainers. In order to attach the wire as firmly as possible, it is first threaded fig. 17. Through a small piece of copper tubing fig. 19. The wire is then passed through he elet, bent and thinned passed back through tube. The wire is then bent back and cut. This method of fixing withstands the greatest strains. In order to prevent the strainer from becoming unscrewed, it is as well to thread a strong piece of steel wire through a whole band, toppes it through one of the eyelets. 2. Wood is the most important material used in building an aeroplane. The framework of the plane is usually made of American pine, although, as will be shown later, the planes are occasionally stretched over a frame built entirely of metal. The varieties of wood used are a few. Materials for construction 41 a number, and need not be described at length. Pine is the most generally used, since it offers a good resistance to bending strains. Unfortunately, it is apt to break. In the early days, bamboo was often employed, but it has been definitely abandoned, since a bamboo structure never possesses very great strength. Whatever its claims on the score of lightness, this wood cannot be recommended, since its shape offers great resistance to the air. At times it may be useful to employ poplar. This wood is very light and very flexible, but unfortunately it warps very readily under strains and under friction of atmospheric changes. Hard woods, such as oak, hickory, ash, are unused in short lengths for the body itself and for the supporting framework of the motor. Some builders favor ash for the ribs of planes. When careful esteemed, it certainly can be bent to an accurate curve. In such a case, it can be given the exact curvature of the plane by means of an ordinary template. Fig. 18. Fig. 19. 2. How to build an aeroplane once it has been bent. It remains set for an indefinite period of time. But if the study of the wood itself need not detain us long, this isn't the case when Weckham to consider the means adopted to utilize its strength to the full. The whole question of strength, in fact, rests on the shape and arrangement of the material. Acting on this principle, Adur, the great pioneer who built the famous Avian Roman III, one invented, with the help of spinazond valure, a process of producing hollow spaces, comparing favorably, in point of strength, with the majority of metals, and greatly superior to everimtal in point of lightness. Adur's Avian, which was exhibited at her Aviation Salon in Paris in 1908, completely justified his claims. The huge wings of this machine could, in fact, bear the entire weight without bending, and this in spite of the fact that the entire structure did not contain a single strainer, and that the wings could be folded back for transport. These hollow space are of varying section. Fig. 20. And Arion Labiltupov carefully selected lengths of would anglude toj the sense of their length by means of a special product, of which the inventor has kept secret. They are used for the construction of the framework. To form a frame, the spars are joined together by a process also invented by Adur and his collaborators. It is obvious that no section of spar could be pierced, as would have been necessary if they had been bolted or screwed together, without destroying the strength of the remaining length of spar. Consequently, the various lengths are assembled in the positions they are occupy, and a long strip of strong fabric, impregnate with a special kind of glue, is tightly one. This aeroplane made the first flight with Ammon on board in history at Sattery on October 17, 1897. It flew a distance of 300 meters. Materials for construction 43 rolled round the joints. By this method, it is possible to produce fully as strong and rigid a framework, as by means of bolts or screws. It frequently occurs that the wood for the construction off the planessus not available, insufficient lengths. In this case, severalling shave tobe join together. This is accomplished by gluing several strips on over the other and alternating the joints. The strips are then fixed with aspicial insoluble glue and bound round with fabric. A much simpler process, but Bonomian saw strong, consists in beveling the extremities off the length down FIG. 21. Toverifanigen sheathing them in a small aluminium sleeve, which is fixed in placebitois small bolts. But this method cannot be recommended, since the aluminium sleeve is very apt to crack when the planes subjected to shock. In every case, the sections used air specially designed toed crease their assistance off air, Fig. 21. These special sections are produced by a machine known as a molding machine, which consists of air valving head provided with several cutting blades, forming in profile the shape of the section required. The Sparus Fidinto the machine and the cutting blades, revolving gathai speed, remove all projecting portions. 44. How to build an aeroplane. 3. Fabric the surface off the planessus constituted bispecially prepared fabric of extreme lightness. Some builders, such as Zen's, a time attempted to cover their planes with chines apartment, but, apart from the fact that it is easily torn, this material isoscily affected by atmospheric moisture, which renders it unserviceable. Rubbered cloth is practicalithian lifabrise employed at the present time. It is vulcanized at a high temperature, which renders it unaffected by moisture. In Europe, it is manufactured by the Continental Company, by Michelin, by the Gutta Percha Co. of Hanover, by Hutchinson Co., the North British Rubber Company, Messrs. Dunlop, and Messrs. Spencer Sons. August tightened waterproof British fabric in Toho's composition, however, India rubber does no tenter, is manufactured by Messrs. Hart. It should not exceed in weight 150 grams 5 Oz. Per skew M1 in England. Mr. A.V. Rowe has used muslin-backed paper with satisfactory results. Eds. Chapter Roman 3. The construction of propellers I. Preliminary remarks. Propeller theories are nowadays very numerous, and all have good points. But unfortunately they do not agree in their most important features, and should always be looked upon with suspicion. The bestandinly wait for many ide off the value of a theoristobled a propeller in accordance therewith and taught it. The result will be conclusive. However, even this method of procedure is open to argument. It is possibly nearly every instance to point out some constructional error. It is therefore necessary, in choosing Amajuso Prandi Tode cone which follows most closely the theory from which it is deduced. Roman 2. Procedure based on M.Dr. Zuik's theory, as Swehave said, when calculating the dimensions of a propeller for an imaginary aeroplane, 1. It is for these reasons that M.Dr. Zuik's theory appears preferable. We have always used it in making propellers, and we have always had good results. It has been shown how the general dimensions of a propeller should be calculated, and it only remains, before examining other ways of doing so, to show how the formula obtained should be played. Dr. Zuik explains in his book how the necessary one seep. 15. 6. How to build an aeroplane templates may be obtained by means of a working drawing similar to that in Fig. 22. On a horizontal axis, O8 pitch constant m is laid off, which gives the point B, on an axis perpendicular to O, starting from this point, lengths equal to mm, 2m, jm, 5m are marked, which giveth points I, 2, 3, 4, 5, 6, which are then joined to the point B. In this way are obtained lines drawn at varying angles to the vertical axis. From the set points I, 2, 3, etc. with a radius equal to of the specific width off the blade, calculated as explained in Chapter I. Arcs are drawn on same city off the vertical axis as the point B, which cut the lines IB, 2B, etc. And horizontal lines are drawn from the points off intersection. The same procedure is carried out on the other side off axis with the same centers, but Fig. 22. With a radius equal to off the specific width, and horizontal lines area gain drawn from the points of intersection. The construction of propellers, 47th efforth side off the templates, which are shown as the shaded portions in the figure, is bounded by the vertical line A. The templates thus obtained are acute out in thin pieces off wood, and the points are a markage upon them at Atties FIG. 23. Tants of off their width. They are numbered as on the working plan, and fixed securely on the board P with their plane perpendicular to that of P, Antithexis J, which is the projection off the blade. All the points mentioned above are placed on axis at the distances jm, m, 2m, etc., starting from FIG. 24. That point O, which thus becomes the center off rotation Fig. 23. The templates, off course, must have been previously curved ta-form segments off the circles obtained bit aching off the center and the distances previously mentioned as radii. It will be seen that these see doff the templates form a table, which determines the shape of the propeller. 48. How to build an aeroplane blade, and after they have been trimmed down where necessary, its construction can begin Fig. 24. From this description it will be readily understood why we have said that Dr's Uicus theory, even if it contains errors, is still preferable to the others, and how it is possible to make templates by exactly following his working drawings. The above method does not give a curvature to the blade, if it should be if the blade satobe curved like aeroplane surfaces. These were certainly in the affirmative, because in both cases the surfaces act in the same way and with the same object. Tatten and Wegner van Dalwitz both say, and we agree with them, that the blade should have a slight concavity, which Sicily made, even in a completed screw, if it is of wood, but where it is built upon a metal framework the cross members should be given that assigned curvature from the beginning. Roman 3. Other ways of designing propellers, the Colix process M. Colix, Thinganeroff, voice in works, follows an empirica method in designing his propellers, and the reader already knows what confidence toplessine results obtained. His method is as follows. The diameter and pitch of the propeller are determined by previously known examples, and first step is taken by finding the inclination of blades at a distance r from the center. A horizontal line OC is then drawn equal to the circumference of circle described by theta of the blade and the dimension of the pitch drawn perpendicularly at C. In this way the point is obtained, from which the horizontal line DG can be drawn. Now, if it is required to know the inclination of the blade at its extremity, join do, and the angle TFJ formed be do, OC give us these were. Construction of propellers 49. If it is wished to find the inclination at a distance RJ from the center, this distance is marked on OC, which give us the point A from a horizontal line is drawn to DC, meeting it at E, and the angle formed be EO, OC give us these were. In practice, the angles this obtained must be slightly decreased tolo for the forward motion off the aeroplane. It will be seen that the angle increases towards Thebos, Fig. 25. And in order to plethuru less given above, the blade should be placed at a distance r from the boss. For this purpose, M. Colix usually makes the length of his blade equal to third off the diameter, and the width of the blade equal to 1/15th diameter. The angles, AIA2 as being known, as well as the distances off the corresponding points from the center, it isasita construct templates to the required shape. The Tatten process M. Tatten's process has a special peculiarity. It consists principally in choosing ascertained diameter, and deducing from it the values of width and pitch. How to build an aeroplane, the Chauvier method, and that of Piskoff and Koechlin might be mentioned, but they're interesting from a constructional point of view, as we shall see. Roman 4. The manufacture of propellers, it has been seen that varion of these methods of calculating that a of a propeller leads to the construction of a sort of table formed by these of templates on which the blades are shaped. What the surface of the blade will be like can't this be seen at a glance. There are many more points, chiefly of a constructional nature, Tobe considered before it is actually made. For example, it has been found advisable to cut off the rearage from the tip of the blade, and this should be done whenever it is possible. The efficiency of a surface meeting the reaches its maximum at an angle of incidence of 45, and it was this fact, not out, which influenced Blériot in giving his flexible propeller blades a width gradually increasing towards Thebos. However, he has no definitely abandoned this type. The extreme ends of a propeller in motion move at a very high speed and at a very slight angle of incidence. But those parts nearer the boss move at a decreasing rate, and in order that the may giving equal thrust, the angle of incidence must be increased. But the speed increases so much faster than the angle of incidence that the canatel ways be counterbalanced, and that portion of the screw near the boss offers a relatively enormous resistance to rotation, which isn't in proportion to the work performed. From this it follows that this portion off the blade should be cute away for a case where it will not affect the strength of the propeller. Propellers can be manufactured in metal or in wood. The first propeller stove made had iron arms. They are nowadays very widely used, and there is no reason the construction of propellers 51 why they should not continue to be so, as they can easily be improved in many ways. At the present moment they are used by the Voisin brothers, Esnault Peltery, the Antoinette Company, Blériot, and many others. Metal propellers a flat steel arm is made and pierced with holes corresponding to those in the blade, which has previously been suitably shaped on thetum plates, and that were then riveted together with copper rivets. Both blades having been similarly treated, only remains to fix them in their place, and for this purpose the steel arms have rectangular or triangular ends, which fig. 26 are affixed in acylar by means of a cotter and nut. The collar can vary considerably in its form, and must be made so to fit firmly on the motor shaft, fig. 26. In the sketch, it should be noticed that the propeller arms are parallel, and not in the same straight line. In many types, however, arms are situate along the same diameter, as in Esnault Peltery and Antoinette propellers, figs. 27 and 28. In our opinion, the best metal to for the surface of the blades is sheet aluminium. A sit can be used in comparatively great thicknesses on account of its lightness, and this tends to increase the moment of inertia off section off the blade, and in consequence it preservates 52 how to build an aeroplane shape. We have seen that the blades are attached to the arms by copper rivets, a great number of which, of course, must be used to form a solid structure, in order partly fig. 27. Fig. 28. To avoid this lengthy operation, Rudolf Chillingworth of Nuremberg has patented the device shown in figs. 29 and 30. The propeller blade is skewed out of sheet metal, fig. 29, with twaddings at its base, which are folded over and welded to the arm. In this way only a few rivets are necessary to attach the arm to the surface of the blade. Often the two blades are cut allen on piece, but this method ISO pent objection on account of the difficulty. The construction of propellers 53 in attaching the propeller to the motor shaft. We cannot pass over the name of M. Chillingworth without mentioning another patent of his for making propellers. The blades are fashioned for out of own sheet of metal, but are reinforced over a part of their surface by a wooden facing, which is attached to the metal by a kind of circular caparum riveted to the blade. This method makes use of the best quality possessed by wood, which is its resistance to bending stress. Fig. 31. Wooden propellers their area certain number of fig. 31. Drawbacks inherent in metal propellers. They are heavy and easily bent, and because of their great elasticity they vibrate when in use. If the burst under the strain of high velocity, the pieces are a great source of danger. It is a matter of some difficulty to attach the blade to the arm and the rear face, however well it may be constructed, cannot be made to show an even surface. For this reason, for how to build an aeroplane it is easier to make wooden propellers, as they have advantages which make them preferable to the others. Wood has greater tensile strength than the best nickel steel. With the grain running lengthways to the blade, the danger of its flying to pieces under centrifugal force is reduced to minimum. Its lightness allows the blade to verific through, and to be shaped in such a way as to for the least possible resistance to motion. There is, moreover, another advantage arising from the fact that the moment of inertia increases as the square of thickness, so that the propeller will offer a great resistance to flexure and can be run at a very high rate of speed. In the event of its breaking, the pieces, being often a great mass, possess very little force and are generally harmless. The inlid back off the propellers is the difficulty of their construction, which makes them very expensive. The best known makers are Messrs. Chauvier, Piscoff F. and Coachland. They can be made in one piece like those of Messrs. Wright and M. Piscoff F., or in superposed thicknesses or lamini like those of M. Chauvier. Both methods require great skill and give good results. On the whole, however, we believe the latter method to be better, as it allows the choice of first quality wood without any flaws to impair their strength, but it necessitates the use of special insoluble glue to unite the pieces securely. The method of construction is as follows. On an axis, Zyra threaded thin strips of wood, I2 and 3, cut out according to the dimensions off the propeller. They are superposed as shown in Fig. 32 and glued together. The projecting edge are then cut away along the line saw BB, after which the blades have tobe-shaped in accordance with the templates. Although his method of construction may appear simple, it is in reality extremely difficult, for the smallest irregularity affects the efficiency of the construction of propellers 55 propeller tone nor mouse degree. When the blades have been shaped, they airpolis hid and varnished. It is obvious that the best shape of blade is that giving a cross-section which combine a strength with the least resistance to forward motion. Sir Hiram Maxim has shown that the section illustrated FIG 32 in Fig. 32 is the best for this purpose. Its greatest thickness lies at about 1/4 of its width from the forward edge, where the greatest pressure is applied. Although we think it desirable to make BB slightly concave, several well-known engineers are opposed to this opinion. See framework propellers. In addition to the foregoing, a third class of propellers must be mentioned. In this 56 how to build an aeroplane case, the blades are formed by arms and cross members covered with fabric. The first propellers of this type were made by Colonel Charles Renard in connection with his dirigible balloon experiments. One, they were formed bit woe lengths of steel tubing fixed to the axis of rotation at woe different points. The cross members over which the fabric is stretched are given a curve suitable to the helicoidal surface. Hatton has designed propellers of this type for existing dirigibles. In some cases, the cross members over which the fabric is stretched are aerially supported by a single steel tube. Fig. 33. D. Other types of propellers. Types of propellers can be multiplied ad infinitum, so that wearable to refer to them all. Mention should, however, be made of the propeller with flaccid blades, which act solely through thection of centrifugal force. The blades consist of strips of fabric, to the extremities of which are attached iron weights. When set in motion, the weights, under the action of centrifugal force, cause the blades to assume their proper shape. Majorvan Parseval actual uses this type in his dirigibles. It is sometimes thought that these flaccid this type of propeller for aeroplane experiments was made in England by Stringfellow about 30 years before Renard. Eds. Construction of propellers. 57 propellers possessed advantage of a variable pitch, but, in our opinion, this would not counterbalance the detrimental effect of the pockets which are formed in B V to K FIG. 34. Fabric during rotation. At any rate, the type is for little used. The firm of August Riedinger Augsburg's patented a mixed type, which nevertheless seems to possess good points. Chapter Roman 4 arrangements for starting and landing General remarks an essential condition in a flying machine is its ability leave the ground under its own power, and in order that it may do so quickly, as well as for ease in transportation, it should be able to move easily over the ground up to the moment of rising. Thus it is necessary to provide some means wheels or skids on which the machine may be readily moved about. These wheels or skids should be fixed to the chassis, which must be so or das to absurd the entire shock off landing. The chassis, moreover, must be flexible and capable of movement in any direction, for an aeroplane when traveling over the ground meets with all sorts of obstacles and is often turned out off its straight course. The wheels should therefore be capable of adapting themselves to circumstances. It is clear, then, that it is necessary to build a good chassis, and that the materials used must be of the first quality, strong and light. Some few pilots employ a system of Rayland at our Orpelin, and launch their machines by means of a falling weight. In our opinion, however, this method will not survive, and we only mention it in passing. Roman 2. Wheeled chassis. The most general way of mounting chassis ice and wheels, set like casters, free to move in all directions. The types, starting and landing. 59. 60 how to build an aeroplane of chassis are so numerous that they cannot all be described in detail. So will only mention those which are most widely used in those fitted to well-known machines. A. The voice in chassis. Fig. 37. The voice in chassis is the oldest now in use, and consists of a rigid rectangular frame of steel tubing. The longer sides of this frame are parallel to the ground, while the others carith forks which hold few heels, and can move a freely in every direction. 2 steel tubes fixed to the frame unite it firmly to the fuselage, and at his time act as receptacles for powerful shock absorbers in the shape of Fig. 36. Helicoidal springs. Tonsure rigidity distrust with tension wires. As thew heels would not run parallel if the forks were free tottern independently. The hubs are united by a jointed rod, and tension springs are stretched diagonally from the hubs to the framework. This chassis has given abundant proof of its reliability and has been adopted by many of the leading aviators. B. The Blériot chassis. Fig. 36. Simplicity is the chief feature of the chassis made by the hero off-channel crossing. The main frame is of hardwood and carries two steel tubes on which thew heel forks slide. A jointed rod similar to that described above keeps thew heels. Starting and landing 61. 62. How to build an aeroplane running parallel. Another type is also shown in the figure, which, though quite good, is not often used. Its extremis implicitos not warrant explanation. See the Antoinette chassis figs. 38 and 39. The Antoinette Aeroplane mounted onto heel spaced closetoj theran secured rigid litithe framework. Add fig. 38. Additional support is provided by buffers projecting beneath thewings. See fig. 39. As this arrangement would be to rigid to absorb the shock off landing. Two long wooden shock absorbers aerated in front of thew heels, which touch the ground before they do, and ease the descent. 1. The chassis has undergone considerable alterations since the above was written. The buffers have been discarded, and thew heels placed further apart. Eds. Starting and landing 63. Such are the chief types of wheeled chassis. They are always constructed off steel tubing, as that has been found to be the best material for the purpose. Their assembling must, however, be conducted with care, on account of great strains which they have to undergo. This is done in several ways, either by inserting thenes off the tubes in cast iron angle brackets and brazing them by cyclofashion, or by acetylene welding thetu bestogther. Fig. 39. In the Snalt Peltieri workshops, the latter method is always used, with their salt that REP monoplanes have a reputation for rigidity. The German Jatho Aeroplane is entirely constructed by this process. Another excellent chassis is that used on M. Karl Hipsich's Aeroplane at Bremen. It is composed of two wheels on a common axle, with toward scarrying shock absorbers, which are both inclined towards the center of the machine, so that, if the landing takes place on wheel, the shock is taken orthogonally by the spring and sustained equally by the whole machine. If a normal landing on both wheels is made, the same result obtains. 64. How to build an aeroplane. Starting and landing 65. The Jatho aeroplane No. Roman 4. Is mounted on a chassis constructed off large steel tubes. That front wheels, furnished with laminate wagon springs, air under control, but the third wheel at rear eye lift free. Every part of the machine is acetylene welded. In all the foregoing types, the aeroplane, or rather its center of gravity, is supported onto a principal wheels, while the third wheel attached to the fuselage merely supports, tail end keeps it off the ground. Roman 3. Chassis with skids. This is the type employed by the brothers Wright, and necessitates thewsy off supplementar means off starting. The Astra Company, Warthesala manufacturers off Wright machines in France, make the skids out of American pine, the strength and elasticity of which renders it peculiarly adaptable to the purpose. They are shaped by being soaked and cayed on plates, which have a slightly greater curve than Theaned desired. After remaining soaked for some days, they are dried, and the wood gradually springs back into its distinct curve. They are rethenretiforus. The chassis is assembled by means of socket brackets, and secured by small bolts, and the skids are affixed under the lower sustainer. The American type of aeroplane is furnished with skids, and those not career wheels. While inconvenient for starting, they are excellent for landing purposes, and for this reason several aviators have devised means whereby the advantage of wheels and skids may be combined in one system. Roman 4. Combined chassis. The first of these was built by Henry Farman. It consists of two pairs of wheels, each pair crossing gasket fixed beneath the surface. Fig. 42. The wheels are mounted on laminate wagon springs attached to 66. How to build an aeroplane. Starting and landing 67. Skids. If the landing is made with a certain force, the springs give and bring the skids into contact with the ground, where their friction brings the aeroplane to a standstill. This device proved most satisfactory at FIG. 42. Chalons, and with a little improvement, should become very popular. The Prinny Bertet Aeroplane, tried at Juvisy, and Herring Curtis biplane, aerial fitted with wheels and skids, an arrangement which, in our opinion, will applied to machines in the near future. Chapter V, the fuselage building in the motor the controls I. Necessary qualities off the fuselage W. have no arrived at he most important part of an aeroplane, the fuselage. 1. It is part that the chassis, the sustainers, the motor, the control levers, the pilot seat, and the controls are affixed. It therefore tobe capable of sustaining any strain, for it is the body, so to speak, of the bird. It is most important that all built fuselage should be indifferent to vibration, able to resist bending strain, and suffer great shocks without damage. The assembling of its constituent parts must be done in the strongest manner possible, for the construction of the fuselage is of as much importance as that of the aeroplane proper. Roman 2. Various types of fuselage there manufacture a fuselage is in fact only able to girder, like that used in many other constructional operations. In aviation, however, it must be able to stand equal strain, and at the same time, be very much lighter than when used in other structures. For this reason, its construction presents a very nice problem. Under different manufacturers, they assume various shapes, which are influenced said by the position of the one fuselages that are generally used to denote the body of aeroplane. Eds, the fuselage 69 peller. If the propeller is in rear of the surfaces, provision must be made for its revolution, as in the voice in biplanes. The fuselage consists essentially of four members, joined by these anthracite by steel wire and strainers. Both wood and steel are used in its manufacture. Wooden fuselage lighter and quite as strong as a steel one, but is more expensive, owing to the difficulty of construction. It is made either in triangular or square section, and in both cases the same methods are employed. A. Wooden fuselage. The templates, cued according to Theplins, are secured temporarily on a very strong spar. Other rods forming the longitudinal members of the fuselage are bent along the templates, fitting in the notches left for this purpose. These rods are then tied with careful chosen pieces of wood, sectionally and diagonally, to omit every possible strain. Fig. 43. After the tie shave being placed in position, the whole frame is assembled in the way invented by Ader and Espinosa, which has been referred to in a previous chapter. This consists of winding fabric coated with glue around the joints. When the whole istry, the templates are taken out and other ties inserted in such a way as to consolidate the whole structure. Finally, several coats of varnish are applied. Fig. 44. In this way along fuselages and truncated fuselages are built. The former serve as the main body of the whole machine, while the latter only contain the motor and control levers. Piskoff F. and Cochlin have built their monoplanes with fuselages which may be compared to the hull of a motor boat. Fig. 45. It is an excellent type in point of strength, but its weight is often excessive. Some manufacturers build their fuselages in quite a simple way, as follows. The four longitudinal members have aluminium sockets attached to them, in which thenes off the lateral members fit. By this means, the upper and lower constructions of 70. How to build an aeroplane. The fuselage. 71. The fuselage are built up separately. It is sassy enough when they have been completed to place only on the other and to join them. Wire stays are attached to the bolts which fasten the sockets to the main members and ensure the rigidity of the whole. It may be remarked. Fig. 44. That this method is easily applied to fuselages with not less than 4 sides. In constructing a triangular fuselage, particular care must be taken to prevent weakening the sections of lower member, which is caused by the insertion of a large number of bolts in each of them. In addition, it would be necessary to pierce the sockets in some of the types, or otherwise the bolts will not be placed regularly as in case of a quadrangular fuselage. 72. How to build an aeroplane. Building in the motor. 73b. Metal fuselage shave the advantage of being rapidly and easily constructed without constant supervision. The Blériot machines are all provided with them. They are made by simply uniting the lengths of steel tubing with corner brackets and joining the longitudinal member there with steel tube uprights. The whole is then braced with wire and strainers in the usual way. See Fig. 46. The fuselages will support a heavy load without bending, but in certain cases they have the drawback of being unable to stand torsion, and while the chassis, the FIG. 46. Sustainers, and the controls area silly supported by them, the addition off the motor requires them to be very strongly reinforced. Roman 3. Building in the motor out in fuselage, unlike those in metal, is very suitable for carrying motors. It is only necessary to replace some off the parts, which will come into direct contact with the metal parts off the motor, by strong girders off torviron. Most aeroplane motors are mounted in this way. In voice in biplanes the motor is placed near the rear end, off a strong truncated fuselage made off hickory, above the lower sustainer. This wood framework is reinforced by side members and for cross members, off steel pierced with holes torjuice thuate. 74. How to build an aeroplane. Building in the motor. 75. The motor is then bolted down onto similar hollow girders placed on each side. In some cases, to avoid the additional construction, the whole off the forepart off the fuselage is built off steel, as in the Bolotov F machine Fig. 47. The mounting of ferrotara motor is much easier. It merely consists of passing the motor shaft through centers oft wo steel cross pieces forming the diagonal so the fuselage into different sections. PLG. 48. Fig. 48 shows the method of mounting an Antoinette motor and Fig. 78. A Nomrotara motor on a voice in biplane. In Antoinette and Blériot aeroplanes the motor is mounted in the same way in the forend off the fuselage. The important point or member in building in motors is not the method for aller similar but the way of carrying it out. Care must be taken that the motor coupless not a can be a weak part of the machine. It should be distributed as fair as possible over the whole perimeter off the fuselage. The bolting down off the motor, it need not be said, must be very carefully done. 76. How to build an aeroplane and frequently overhauled. A loose bolt in so fragile a framework may easily cause disaster. The Wright motor is very simply mounted onto a stout piece of wood attached to the lower sustainer. This arrangement goes away with the need for any fuselage, and only requires the sustainer to be strengthened where the motor rests. It must not be forgotten, however, that while it may be quite adequate owner, Wright aeroplane, this mounting would not do machines. Most aeroplanes are driven by a single propeller, which sets up a tremendous torque with its lever point on motor bed. If this point is situated on the sustainers, they very soon wear out. It is not quite the same in the case of Wright machine, although even there the contingency exists to a certain extent. However, this way of mounting motors is not likely to endure in the future and isonly convenient for experimental work. Roman 4. Arrangement of the controls. The various movements of aeroplanes in the vertical and horizontal plane air brought about by altering angli of incidence of certain surfaces, which are hinged and moved in their quire direction by lever or wheel controls. The rudder planes are stretched on framework, and are easily controlled bicables led over small pulleys and connected with arms rigidly attached to their surfaces and projecting from each side. By moving them so opposite a portion off their surface to the end, the pilot is able to guide the machine. This movement is accomplished by levers, which are capable of very easy and delicate operating. Either hand or foot control can be used. The former is generally reserved for warping the surfaces or for operating the ailerons, up in which the lateral stability controls 77 pens, and which must be performed with the utmost nicety. The turning and elevating motions, calling for less care, are performed by double armed levers, which combine both these movements in either direction. It may be remarked that Thusiofkables to manipulate the controls necessitates a duplicate set, because of the FIG. 49. Cannot be reversed to pushback after being pulled forward. Therms, therefore, fixed to the rudders and ailerons previously referred to, must project on either side, and have cables attached to each end in order to give positive and negative movement to the surface. Control levers, which are placed by the pilot's seat, must move easily, but not involuntarily. The use of a fuselage has the great advantage of allowing the pilots. 78. How to build an aeroplane seat, the controls, radiators, etc. to be easily disposed. A sort of platform can then be made on which are mounted steel supports carrying the bearings off the controlling mechanism. The voice in fuselage is well add in this respect. A Fig. 50. Single steering wheel controls the movements off machine in both the horizontal and vertical planes, the former by being turned to the right or left, the latter be being pushed toned fro. The elevator is mounted on a prolongation off fuselage, Fig. 37 4 mid-bit waplatester net upwards. Controls 79 in which aromatit woholskiving passagetethixison, which the elevator rocks. Aerodrigidly connected to thysaxis, ishinged otherodic shuate bathido and fro movements off the steering pillar. The antoinet utilizes the whole length off the fuselage, carrying the aluminium tube radiator, invented BM levavasseur one other side. The steering wheel sare one other city off a comfortable pilot seat, Fig. 49. In Blériot aeroplanes, the controls era most interesting. A single steering pillar is used, capable of movement in every direction, and hurrying Galerjane Verted cup. To the sides off the scupcables area attached, which pass over small pulis and aero-connected to the rudders and ailerons. The inclination off the cupanana direction tightens on off theckables, and consequently affects the desired maneuver, Fig. 50. Piskoff and Koechlin, assuming that in flight the pilot always tends to maintain his body in a vertical position, have invented a pilot seat which can oscillate backwards and forwards. The elevator is actuate by these movements, which therefore should ensure automatic equilibrium. Textgenov controls is obviously own, in which the ingenuity of various constructors has full scope. In fact, many other contrivances have been devised, but the majority of them are impracticable. Chapter VI the plane's eye. General remarks after the fuselage, the chassis, and the motor have all been assembled. The machine is nearly ready for flight. Iten lilacs the planes which are ever difficult to manufacture for monoplanes, and in little less difficult in the case of biplanes. The planes, though very light and presenting a large surface, have to support the entire weight off the machine, and while they must be flexibly to sustain without injury the shock offlanding, they must also be strong in auto kept their shap under the pressure off air. Wood or steel is used to fulfill these conditions in various machines. Roman 2. Biplane surfaces the biplane takes the same placine aerial locomotion as the wheelbarrow does in the history of land travel. It was first form of dynamic flying machine to carry men through air. It has been very much improved nowadays, and is being built by almost every manufacturer. The Wright planes are made by the Astra Company in the following way. 2 flat spars 12.5 m. In length are placed parallel to each other at a distance of 1.35 m. apart, and have their foredge rounded off in order to for less resistance to. The planes 81 the air, see Fig. 51. The ribs are constructed off 2 flat members, curved in the manner previously explained. Small blocks off oak nailed between them preserveth his curvature. The rear ends off the ribs are not secured, but are permitted to slide freely only on the other, thus yielding to a sudden air pressure put upon them. Thea Akblick miscrewed in to the front spar, and the ribs which are made off ash nailed onto it see Fig. 51. The rear spar, being much flatter than the front one, is nailed in place between the rib members. Sometimes the ribs are cut out of planks centimeter in thickness, and joined in front by a piece of sheet metal Fig. 51. 14 centimeters in length. In this case there are spars nailed over the rib members. The surfaces, when finished, are united by a system of upright members which has been patented by the Wrights. Rigidity is inserted by means off iron sockets which hold things off the upright and prevent them from moving by means off a small bolt b. Fig. 52. Things off uprights contain a slight concavity in order to clear the head off the screw V which fastens the socket to the main member or spar. The top sides off the sockets are bent over and splitto receive the wire stays, which are secured by split pins G. Things off the right surfaces must be capable of being warped, and must be hinged, and so movable structure is necessary. This is shown in Fig. 53. The parts G and hair capable of movement relatively to thebold. F. 82. How to build an aeroplane. It is clear from the above that the methods used by the Wrights are very economical and applicable to by Fig. 52. Planes. The surfaces, moreover, are constructed very solidly and easily warped. Fig. 53. The voicing surfaces are constructed in their general lines after the same fashion, but as thiorenic capable. Planes 83 off being warped. They are much more rigid than those of the Wrights. The uprights are fusiform in section and carefully polished. The sockets which connect them to the surfaces made of aluminium, and fixed toth mainspars with eye-headed screw bolts, which also serve to receive the wire stays, Fig. 54. Sometimes ordinary bolts roost, on which small steel connections forth wire stays threaded before the screwed in top position, where bamboo is used forth prights, a special way of assembling must be employed. The socket in such a Fig. 54. Case is composed of 2 pieces of iron bound tightly together with steel wire. Thinned off the bamboo is slightly tapered with a file, and a piece of wood inserted to prevent crushing. But however great the care that may be taken in assembling, a bamboo structure cannot compare the point of strength with hickory or pine, assist in voicing machines. Roman 3. Monoplane surfaces. Monoplanes are the most interesting from a constructional point of view, on account of the problems that they offer. The framework of their surfaces is quite a remark. 84. How to build an aeroplane able. The surfaces have for a long time been made in wood, and this method is still adapted in many cases, but steel also has recently come into use. The surfaces of Antoinette monoplanes are entirely made of wood, and all the cross members are of the same thickness. Fig. 55 shows the fineness of the construction. The main spars are of sufficient length to allow them to be joined together and secured to the fuselage. The ribs in this case are composed of within laths, with ties placed between them at intervals throughout their entire length. In other machines it has been found better to cut them out of solid wood and pierce them with holes. Thewings of Blériot monoplanes are built to fribskit from wood 1.5 centimeters in thickness, which are inserted in a strong steel tube, with 1/3 of their length projecting in front of it. In this case, the steel tube performs the same office as a propeller arm. In order to strengthen the rear portion of thewing, 6 transverse members are placed parallel to the steel tube, and it heans off the surfaces thin strips of curved wood are placed, to hitch the covering is attached. The Esnault pelleterie machine is entirely two of steel tubes oval thicknesses welded together. The Jatho and Hipsisch Aeroplanes in Germany, of which we have previously spoken, are made in the same way. After the wingshave been made, they are fixed to the aeroplane in such fashion as to unite them firmly to the fuselage, and the connection reinforced by a system of wire stays radiating from a mast in the fuselage. To facilitate this, holes should be provided in the steel tubes off the framework, or better still, rings brazed on before the covering is attached, so that the wire stays may be fastened to them. The surfaces are covered with special fabric of which we have spoke 9th chapter in materials. The application of this fabric to the framework is an extremely delicate operation. A sit must be stretched evenly, planes 85 and present a smooth surface. There are several ways of doing this, either by gluing it onto wooden edges or balancing it. Wright always uses simple methods. Marilyn nails the fabric on the crossbar sandribs, upholsterer fashion. The operation of gluing the fabric must be performed with care, as it is very difficult to repair any mistakes. 86. How to build an aeroplane. It is excellent for the machines which are not likely to undergo any alterations. Buten generalitis best that fabric should be laced. If thighs is stone, when there is a wing tube repaired, the covering can be taken off and replaced afterwards. On the voicing machine, the whole of the covering is laced. Buten lithe tail off, Antoinette is striated in this manner. The fabric off the wings is stretched on, glued, and then varnished in order to minimize the skin friction. In case where the surfaces are warped, the direction in which the threads off fabric run is of importance. The weft should lie parallel to the line of Folksure. The Wright have adapted this method in their biplanes and patented it. When the fabric has been placed in position in a monoplane, it only remains to stay the machine, which is done by joining different points of the wing surface at the fuselage by steel wires. This tends to preserve their shape while in flight. These wires are often attached to the end of a very strong upright fixed in the fuselage, as in the case of Blériot XL, in which the upright was a steel tube with fur supports. Roman 4. The curvature of the cross section of the wing surfaces we have not previously stated what form the ribs of the wing surfaces should take. It is, however, of utmost importance, and a point upon which the efficiency of the aeroplane depends. Formerly, they were true planes, containing no curve whatsoever. Experience showed later that the lifting power under these conditions is a great deal less than when the surfaces have a curve, with its center nearer the forward edge than the rear. Nature herself provides us with exempli of this in the Wingefaberd. Lilienthal, the great German pioneer, was first to show the properatio between Thierkopfthekurve and planes 87 the surface. Hegevatus on 12th off the width, and expressed the opinion that the curve should reach its highest point near the forward edge off surface. The Cephagurus were arrived at bestudying birds, and in the Aeroplane off Captain Ferber and Wright Brothers they have proved their value. However, we do not think they to be accepted without reserve, for it is not our purpose to copy birds. Nature has fashioned these wonderful creatures, who nevertheless cannonly fly when they are perfect. If we copy them at all, we must reproduce very part of them so stubtain the same results, beautis we cannot dothise, we must follow out our own ideas. In our opinion, we ought not to copy the curve of a bird's wings, because the thigh provide both for flapping and gliding flight. Not comparison can this be made to our aeroplanes, which only glide. Moreover, according to Professor Mary, head off a bird follows a sinuous course, tolo for the variations, in their lative positions, off the sustaining force and the center of gravity. The wings, of course, reproduceth this oscillation, which has no parallel in aeroplanes. It follows, then, that careful experiments should be made before adopting a curved surface. Fewer of laboratory is better in certain cases than the easier method of observing nature, and results of the experiments of Sir Hiram Maxim are of more value for aviation than the works of Mary, Mouillat, or Pettigrew, interesting though Thabe. But the curve of the sustaining surfaces has not the importance with which it is usually accredited. The wings of Antoinette are absolutely symmetrical and very efficient. What ice of importance thingle off incidents off the plane. The same problem has already been faced in hydraulics and thermodynamics in the case of steam and water turbines. The fluid, whether of air or water, must flow regularly around the surface without disturbing its continuity, and it must split the energy. 8. How to build an aeroplane due to its velocity vintage parts, the not producing resistance to forward motion, and the other driving lift. A curvature off a proper shape should increase the latter and decrease the former. The air should then leave the surface with the vertical velocity I, so snatointerfer with the following masses off air. In a word, fourth curve should be good one. The air must be pressed downwards as soon as it reaches the surface with this constant velocity, and in order to produce a lift I toto possess an uniform acceleration, which will compensate of and preserve its minimum value. It I sassatorjuice, these considerations tone equation giving a parabolic curve, which must have its highest point near the forward edge. From this it can be seen that the parabola, which already possesses astonishing qualities both in optics and physics, retains them in aviation also. In addition to those mentioned, one occasionally meets with curves of an extraordinary nature, arrived at be practical experiments, and sometimes without any theoretical grounds. But no good results can be obtained by the construction of aeroplanes on these lines. Chapter Roman 7 motors the theorethat the aeroplane motor must of necessity be of extremoliteness as a fansion origin. It was confirmed by the late Colonel Renard, who expressed the opinion that artificial flight would only render it possible when the weight of the motor was reduced to kilos. 3 ibs per HP. Even at representime many engineer sacrifice reliability taliability, with the consequence of that the working of the motor is seriously affected. When will it be understood that the best motor for an aeroplane is ordinary motor Kerngen, with its weight suitably reduced? Figure S are the best proof. At Le Mans, Wilbur Wright flew with a Passenger weighing 100 kilos, 220 ibs, Bymian's OFA 25 IP motor. His motor might, therefore, equally will have weighed 4 kilos, 8 ibs. More per IP, at Issy Blériot in his monoplane no. Roman 12, flew with an extra weight of 240 kilos, 530 ibs. Driven via 35 IPE, NV, motor weighing 77 kilos, 170 ibs. He could therefore have flown with a motor off the same power weighing 77 240 317 kilos, 700 ibs, or 9 kilos 20 ibs. Per IP, saw that Colonel Renard's figurous need not be seriously considered. On the other hand, It would be mistake to overlook the importance of the reduction in the weight of the motor. For the future, it is sofqual, if not of greater importance than was the case in the olden days with the motor car. It is perfectly evident that the lighter the motor of an aeroplane, the greater will be the quantity of petrol that I know how to build an aeroplane can be carried, and consequently, the greater the distance it can cover. At a future period, when small machines designed to carry only own person are being built machines that will really be equivalent to the motor, bicycleth lightness of thing will be of great importance, since it will enable the span, the total weight, and consequent the cost, to be reduced. But it is unquestionably a mistake to hold that artificial flight in itself is dependent on a motor, of excessive lightness. From a wholly different point of view, however, reduction in weight of the motor is not to be decreed, since it has sold and will in future lead to interesting discoveries. Reduction of weight was first achieved by manufacturers by cutting down their material, angles were rounded off, shafts and connecting rods were cut down to the lowest possible diameter. In some case, new systems of cooling were invented. In others, the flywheel was suppressed. Subsequently, when the structural material could be reduced no further, the very principles in which the working of the motor was based were revised. Two cyclomotors made their appearances automobile racing was nearing themed off its vogue. Since Yuhin, we have seen in succession rotary motors, valveless motors, and a host of other interesting types, which, by going to the route of motor design, have paved the way for the discovery of several new principles in practice no less than in theory, until no we havenly considered the internal combustion motor driven by petrol. At present time, it is the only engine universally employed, and in all probability the type will endure for many years to come. It is the enormous advantage that its fuel, petrol, is exceedingly light. Its flexibility, moreover, is increased every day with the application of new inventions. Its solitary drawback, which Bethue seems to have very little terror for constructors, is that it entails a high speed of rotation, which necessitates the use of transmission by bevel or chain, both of which absorb a good motor's 91 deal of power and lower, the efficiency of slowly revolving propellers are used. On the whole, however, this drawback isn't very serious, for in practice we have seen that aerial propellers can perfectly well be mounted direct on the shaft. Nevertheless, attribute should here be paid to the lifelong labors of that great pioneers, Clement Adur and Colonel Renard, to whom is to the credit of having reduced the weight of the steam engine at its lowest point. One the marvelous steam engine able be Adur for his Avian Roman 3, with which he flew 300 meters at Sattery, can still be seen at He Conservatoire des Arts et Métiers in Paris. Colonel Renard also built a very light steam engine at Chalet Meudon, whose most remarkable feature was its Aero condenser, and he was, moreover, the first to propose to apply the electric motor to aerial vessels. The first airship which was dirigible in fact as well as in name, La France, carried a dynamo supplied with electricity from a wonderfully designed battery, which to this day has never been surpassed. To this reference to the electric motor we may hurried that the discovery of a light magnetic metal would render it immediately applicable to aviation. All thought his is mere speculation, for the present at a leavance, it may be observed that, should this problem ever be solved, the aeroplane of the future would be propelled simply by an armature in motion between two electromagnets. And since we have embarked on speculation, I may mention that the time is not far off when the wireless transmission of electric energy through space, by Hertzian waves or other means, will be realized. The experiments along these lines of Mr. the late Professor Langley and Sir Hiram Maxim, as a matter of fact, both reduced it further. The former, in 1901, built an engine developing 1 JIP with a total weight of just under 7 ibs. The latter, in 1894, built a couple of compound steam engines, weighing together 640 ibs, and developing a total of 362 IP, or ejib, per h. Eds. 92 How to Build an Aeroplane Marco. Anthony with Amadel Dirigible, and of M. Gabbett with his submarine torpedo, indicate that this problem is almost solved. The ideal motive power would then have been found, the more so since the velocity of rotation of the armature could bevered be means of a simpler rheostat. For the present, however, these Arion dreams, who swing Sari up Takarion farther even than those off an aeroplane. It would, after all, perhaps bibiter not temptotain thadial at a bound, but rather, todvin semethodically, contenting ourselves for the moment with the internal combustion motor, and seeking rather to perfect it. The internal combustion motor owes its rapid development to the motorcar, and the aeroplane motor has been evolved efforts off those workers who sought to reduce the weight off the Geneinvented by Daimler. Many engineers shave worked at he problem, with the result that it has been solved in several different ways. Any atom toadscribe indeed every aeroplane motor would inevitably increase the length of this book beyond all possible limits, so that we shall confine ourselves, firstly, to description of the general characteristics of the aeroplane motor, and secondly, to more detailed account of some of the best known types which have already been successfully tried in flight. To reduce the weight off the motor kerngen, and so producing aeroplane motor, the first necessity was to suppress the flywheel. This was accomplished by increasing the number of cylinders, whose pistons act in succession on the motor shaft, and surrendering the work exerted on the shaft more constant. By this means the necessity for a flywheel, which is designed to store up power at the moment when it is at its highest, in order to yield a tup again when it is become negative, is abolished in principle. Further arises the difficulty that a large number of cylinders requires a corresponding increase in the length of shaft, which is therefore weakened if motors 93 the same section is retained. This difficulty has been overcome in practice by various methods. Some manufacturers, such as M. Levasseur and many others, have disposed the cylinder cinturos, inclined to each other at an angle. This is V-shaped arrangement. Others, particularly M. Esnault Peltery, have adopted Thefn-shaped arrangement, which very greatly reduces the length of the shafts. These motors will be dealt with in detail later on. This, then, was the origin of the motors with V and fan or star arrangement. Butte another type, off motor has lately become prominent, and displayed a part in some of the longest flights yet made the rotary motor. This motor possesses the enormous advantage of dispensing with water cooling and itchy accessories. Its high velocity of rotation in the air in itself produces all the cooling that is necessary. There are grave difficulties in cooling a motor with fixed cylinders, on account of the directly opposite requirements of the radiator and the aeroplane. If the radiator is placed orthogonally i.e., at right angles, to the direction of light the cooling is excellent, but the resistance to the air is enormous. If, on the contrary, the radiator does not meet the air with its full surface, resistance is diminished, butanely at the cost of rendering the cooling inefficient. Where a therefore placed on the horns of a dilemma. In voice in aeroplanes the radiator is placed transversely to the direction of light. Other builders, on the other hand, place the aluminium tubes laterally along the length of the body, as in the case of Antoinette monoplanes. In other cases, again, the superficies of the radiator is utilized as a carrying surface. Several fixed-cylinder motors, finally, air-cooled by a current of air forced through a surrounding jacket by a ventilator mounted on shaft. But in every case, air finally brought back to the same result, that cooling isonly obtained at Helosoft power. 94 How to build an aeroplane. Hitherto we have only referred to the means adopted to lighten the motor that air outwardly visible. But many other methods have been tried. In some motors, in fact, the carburetor has been suppressed, and the petrol is implied into the cylinder head by appropriate means. This is the method adopted by Levasseur in Antoinette motor. Another new departure-ain motor construction, originating in the development of the aeroplane motor, is the arrangement of the valves required in the rotor motor. Some of these will be mentioned in the detailed descriptions of the various motors. Methods of ignition, finally, offer a wide field for active experiment. The same holds good for many other departments of motor design, so that we cannot doubt the eventual perfection of the internal combustion engine, height at a level of excellence already attained. This brief study of the motor question is concluded by a description of some of the leading types. Fixed-cylinder motors. A. Antoinette Figs, 56 to 59. The Antoinette was the first of aviation motors, and Evan off-light motors of free description. In former days, the Antoinette motorboats carried off many of the great races. Even at present time, this motor is the lightest of all, and was used in the first flights off Santos Dumont, Farman, Blériot. Its design, Dudo M. Levivasseur, presents many interesting and ingenious features. It belongs to the type, already mentioned, in which the flywheel is replaced by a large number of cylinders, mounted in the shape of a V. The number of cylinders varies from 8 to 16 and 32. Its exceeding glillo weighed about a kilo, 2 ibs. Per I piss forcibly illustrated in the extraordinary photographofa, Mankaring gani off these 100 IP motors on his shutter. Motors 95 feet which may well be compared to Atlas upwarding the world. The forged steel cylinder circuled bewater, circulating within arid copper jacket which is deposited round, the cylinder walls being electrochemical process which give a sash sheet of extreme thinness. It is well known that FIG 56 different metals expand in different degrees when subjected to the same temperature. In order, therefore, to neutralize differences in expansion which are set up when the motor is working, fuels off the copper jacket contain what may be described as scaffold, which allows them to stretch if need be. The motor is bolted to the aeroplane frame in the simplest manner, as in the dinar motor car. The screw propeller is mounted direct on the crankshaft outside the crankcase. The water-heated beacon. 96 How to build an aeroplane tacked with the cylinder walls is rapidly cooled through being passed through a radio condenser, and the drops off water condensed in the aluminium tubes are collected and FIG 57 pumped back into the tank. Aluminium tubes, 4 meters in length, arranged laterally along the sides off the body, compose the radiator. The petrol is fit erect into the FIG 58 cylinders in the quantity required for each explosion by a distributor. The Antoinette motor therefore possesses several novel features. On Latham's monoplane already. Motors 97 rendered a brilliant account of itself. The type most generally employed is 8-cylinder 50 EP, the strength of which is indisputable. After manies for accident, when the remainder of the machine has been reduced to a state of wreckage, the motor has been found intact. B. Anzani Figs 60 and 61, the famous monoplane Blériot XL was driven by an Anzani motor on its cross-channel flight from Calais to Dover. In its design, a ream-bodied manufactures derived from M. Anzani's FIG 59. Year-long experience of motor bicycle racing, strength and reliability its chief qualities. Aluminium is dispensed with as fair as possible, steel and cast iron being its chief structural materials. It is cooled bethection of Theron fins. The cylinders are arranged fanwise and inclined to each other at an angle of 60. The method of ignition renders equivalento motor with 6 cylinders placed starwise. In consequence, the motor cup lies extremely regular. The most general type is 6-cylinder 24 IP. 28 How to build an aeroplane Fig 60. Fig 61. Motors 99C. Esnault Peltery Figs 62 and 63. The REP is perhaps the most carefully designed of existing light motors. The composition is remarkable from every point of view, starting with the simple laws of the structural strength of various materials, and drawing up in his wide FIG 62. Knowledge of the most recent developments of metallurgy. Esnault Peltery has succeeded in producing a motor, which give us a maximum IP with a minimum weight. The strength of materials never exceeds a certain value. Hitherto the strength has only been calculed to furnish the highest possible result during a small fraction of time. Esnault Peltery has started from the principle of lengthening the duration of the maximum effort, and how to build an aeroplane has succeeded in utilizing the whole force of cohesion of metal. From the point of view of its working, the REP motor needs no special mention. Its construction alone deserves attention. The cylinders are arranged fanwise and octanthosama crank. Ignition is by high-tension magneto. DENF Figs 64 and 65 on June 3 Ardolph last year, when Blériot flew with trois passengers at Issy, near Paris. His monoplane was driven by an ENV motor. It was FIG 63, the same monoplane, no, Roman 12. That was destroyed by fire at Reims last summer. The life-feature that calls for special mention is lubrication, which works very efficiently by a pump which causes a continuous circulation of oil on the frictional surfaces and is regulated by a float. The cooling is effected on the same principle in Antoinette motor, Bywater circulate engineered copper jacket. The most usual type has 8 incline cylinders, IUM M Borby 130 mm stroke, and develops 50 IPAT 1000 rpm. Its weight is no more than 75 kilos, 165 ibs. There's 101 the crankshaft Ishalo, and Thuebs Eridus Pinsed with in favor off discs. Fig, 64. E. Gabaron Fig, 66. The Gabaron motor embodies the famous principally of opposed pistons, which gaverize FIG, 65. Tossa much discussion at Hetheim off Grand Prix motor races. It has 8 cylinders placed crosswise, each 102. How to build an aeroplane cylinder contains a pair of pistons working in opposite directions. The motor develops 80 bpand, weighs 150 kilos. Its fuel consumption is no more than 35 cubic centimeters per IP hour. It has been used on Breguet Gabron aeroplanes. F. Duthdill and Chalmers. Fig. 67 on M. Santos Dumont's miniature monoplaneth is given proof of excellent qualities. It is noteworthy by reason of the small space it occupies and the implementer in which it can be mounted on an aeroplane. The cylinders are horizontal and opposed. A point to be noticed is excellenthemispherical combustion chamber, which is motors 103 devoid often a space that can interfere with the perfect explosion of the mixture. They nishanofet cylinder is absolutely independent off the top the others, so that the motor is started with the greatest ease. The position of the cylinder absorbs nearly the whole of the vibrations, so that the motor can be mounted on every lightest and most fragile of machines. It is built with 2, 4 or 6 cylinders, opposed in pairs, and working on a crankshaft with 2 or 3 throws placed at 180. G. Farcott. Fig. 68. This motor isofentire novel design. It has 8 horizontal cylinders, placed starwise around a crank chamber which contains the vertical shaft. Cooling Gispier fins, but isided Bielerge ventilator which propels Aerontotham. Thean Lidraback off this methodes, that it causes the loss of Fapartoth power that could otherwise have been Uli KSFD for propulsion. The inlet valves are particularly ingenious. No aluminium is used in the construction, and the strength is kept impaired. This motor is sold in the following poses 30, 50, and 100 HP, which weigh respectively 40, 50, and 98 kilos, 88, no, 216 ibs. H. Clerget this motor, which is mounted on Tatton's aeroplane, belongs to the class of motors with cylinders placed starwise in a horizontal plane. The fly wheelies situated outside the crank chamber, and horizontally above the motor. To M. Tatton's great annoyance, this gaverize. For how to build an aeroplane taught a curious error that his aeroplane was fitted with a gyroscope to ensure stability. I. Other types space forbids us to describe separately each remaining type of fixed cylinder motors. Among the better known are Renault, Wright, Buchet, Bayard Clement, Panhard Levasseur, etc. In France and Argus, Neckar Sulmer, FN, Pipe, Fiat, Cording, Ellehammer, Fig, 68, etc. In other countries, Fig, 71 and following. Their general features are rendered clear by the photos and diagrams. Special mention should, however, be made of the 3-cycle Corvin and Rybakov motor, which was exhibited at Hess Salon of 1908. Roman II. Rotara motors until now, Thean motors dealt with Erithos whose cylinders are fixed to the chassis, and which Ericuledby. Motors 105 Fig, 69. Siddeley Walsally motor. Fig, 70. Siddeley Walsally motor. 06 How to build an aeroplane various external methods. Award remains Tobset of the motors whose fixed shaft serves as an axis off rotation FIG. 71. Wright motor. Fig, 72. Wright motor. For the cylinders, these are known as rotary motors. By their high velocity off rotation, these motors have undoubtedly solved the problem of air cooling, but on. Motors 107. J. Fig, 73. Wright motor. Fig, 74. Pipe motor. Fig, 75. 08 How to build an aeroplane FLG, 76. Rumpler motor. Yig, 77. Ellehammer motor. Motors 109 other hand. It is evident that in their case the feeding off the petrol into the cylinder santhanician air points off much complexity. Satisfactory rotary motors, a Samatter FIG, 78. Off fact, have no existed until the last few months for previous engines of this type, such as Burlet, only pointed to success. Great rhymes Aviation Week last, first demonstrated that the rotary motor, how to build an aeroplane had arrived, and would last for the next few years, even if it should not prove to the motor off the future. The fine flights off Farman, Paulhan, Sommer, and others have demonstrated this fact beyond dispute. The best known off-rotara motors is Gnome, which still holds the world's record of 4 HRS, 17 mins, 532 5Cs, FIGs, 78 and 79, the 7 cylinders, bolted toe-crank casa-turning FIG, 79, round the shaft which is fixed to the body. The enormous centrifugal force developed during rotation off-course requires the bolting toe-been commonly perfect. To prevent irregularity off-working, the valves had to be assigned in such a way that their action wasn't interfered with by the centrifugal force. These various features have been successfully incorporated in Gnome engine and have rendered Itone off the most reliable motors in existence. To the best offer knowledge, knew the rotary motor has given satisfactory results. This, then, concludes our examination of the Aeroplane motor. Should their narrator motors in desire further information on this question, heckin' don't know better than consult those works that Erin Tirelide voted to the subject, toj their with the catalogues of the manufacturers. In conclusion, we hazard the conjecture that in future the petrol motor is likely to be superseded by the explosion turbine, which would give us, wait, power sun-dreamed off today. After Roman 8 the future, the chief aim of this book has been to give the general public hathero, understanding of the true nature and possibilities of Kanaka flight. But this aim cannot be realized unless Wegland's brief fly at the radiant future that stretches before it. Born a sit was years ago, aviation has not yet attained a sufficiently advanced stage of development to ever remember off the public to grasp its enormous future influence on commerce, sport, and warfare. All that had I may still be removed when we shall witness the passage of some aerial liner plying between Paris and Tokyo. In a short, while a few months we shall see the sportsman and the tourist winging their flight over the countryside. For with Lilienthal, they are seized with the vague longing to glide along noiselessly in a majestic flight, high above the green forests and blue waters. One aviation has made this dream come true. Even thought Aeroplane should possess a purely commercial future. It ascertained that aeroplanes will be manufactured in large quantities for many years to come. But for every long the motor care off the air will have become common, and largely patronized an account of its speed and unique qualities. Aviation will develop, as the motor carted a few years ago, with astonishing rapidity. Before 10-year shave elapsed Thelisand regulation soft, air will have one Otto Lilienthal, der Vogelflugels Grundlage, der Fliegkunst. The future 113 passed into the daily life of the community. The Aeroplane will be common as a bicycle today. Its low price due to the fact that the motive of power will gradually decreased will bring it within their atch oferion. Is it likely that the dream of many inventors will ever be realized that the Ariel bicycle, cycloplane, aerocycle, or whatever it may be called will ever become a fact? We cannot believe it, although it would be unwise to make a dogmatic assertion on the point. Reliable experiments have proved that the muscular power of famine is hopelessly insufficient to raise the necessary weight. No doubt, in future, flight will be possible with Varillo-powered motors, 3E porvenless, but we firmly believe that the reducible minimum must be fixed at 105 km/s, that is, 2 IP. Off late years many discussions, which fourth agreeator Parthave reached no definite result, have raged round the question of what form of machine will eventually survive. Strange to say, the very success of the Aeroplane has brought forth a class of inventors huckling desperately to their petidias in the face of evidence. When will the ornithopterists, the entomopterists, and the other visionaries, whose names indicate the creature whose method of flight they seek to imitate, understand that Aeroplane forms the only economical solution of problem of aerial navigation? The screw propeller, according to them, is advis which wastes the power transmitted to the motor. But this argument is utterly false, and need not be refuted. Then, in addition to their onslaught on the screw propeller, they assiduously sect to prove that Aeroplane glides on the air, but does not fly. What matters the precise way in which it is sustained so long as thighs is economical and safe. Side winds and eddies aerial ready overcome with e-spine devices, and the stability of the aeroplane ability day increased. The flights of Farman, Latham, and Paulhan have, and for how to build an aeroplane adequately proved the security and efficiency of the plane gliding Gonthier, which isn't likely to be surpassed by a system of beating, rotating, or gyrating wings. What is the object of these contrivances, which are based on complete ignorance of the laws of mechanics? Therananity would be obvious and if their inventors wouldn't embed them in our king model. Hereditobe converted to the practicability of an ability, in the same way in which we converted those who scoffed at aeroplane by actual flight. A samatter of fact, the alternating mechanism of the wings would absorb 4/5 of the motive power, which therefore would be insufficient to procure a sustentation. The hopeless impracticability of the ability wing machine could be proved by many other excellent reasons, which, however, are too long to down here and sufficiently obvious to a very sensible mind. The aeroplane, then, is the practical aerial machine, nor is it difficult to decide between their respective claims of the biplane and monoplane. From the mechanical point of view, the monoplane possesses greater efficiency. In stability it can be made the equal of the biplane, nor has it any greater difficulties of construction. The monoplane alone will survive. Its high speed will render it indifferent to atmospheric disturbances. Its stability, therefore, will be perfect. Eventually, the monoplane will be able to attain enormous speeds up to 150 and 200 miles an hour. Every point on the surface of Earth will be brought within reach. Communication will be rapid and constant. Frontiers will disappear. And nations will have approached within measurable distance of utopian international peace. Appendix motor, one of the most reliable aerial motors of British or foreign manufacture, is the Green engine. It operates on the four-stroke cycle and has four separately mounted vertical cylinders. Each cylinder is cast integrally with its crown and vertical valve chambers in high-grade steel, and is machined both on the exterior and the interior. The valves are situated in the head. The cylinder shave polished copper water jackets, devoid of solder joints and seams, and proceed from a single piece of sheet metal. The method of attaching the jackets to the cylinders is quite original and provides for the contraction and expansion of steel cylinder and the copper jacket independently of each other. The circumference of opening in the jacket for the inlet index host valves forms metallic washers for the joints. So the jacket may be removed and replaced with ease, and without in least impairing the sealing qualities of the joints. The valves are off the mushroom spring-closed type in detachable cages, and are operated by an overhead camshaft. The undoing of clamping screws allows of the case being rotated to sufficient degree for purpose of obtaining easy access to the valves and cages when one of them has to be removed. The journals of the crankshaft have a bearing between each throw. Inside the crank chamber, the upper half is webbed between each crank as usual. Cast integrally with each of these walls is a pair of solid columns, which are in 6 how to build an aeroplane drilled out. Passing through to holes thus formed are bolts which serve to tie their cylinders mounted on the crank chamber and the crankshaft bearings. The magnetoned the water circulating pump air placed in the sama lineed immediately in front off crankcase at right angles with the crankshaft, both being driven by worm wheels direct from the crankshaft. The general lubrication of the engine is effected in an entirely novel manner, a simplicity sufficient. Fig. 80. Running the entire length of the interior, off the crankcase on side, near the top, is the main oil channel casts a lid with the crankcase, through which oil is forced by a small gear pump through leads at right angles communicating directly to each of the hollow columns through which the bolts pass, and thence to the main bearings and crankshaft, which is shallow. The reduction of the diameter of the central portion of the bolts allows of sufficient room for the free flow of oil to the main bearings, from which it passes into the hollow crankshaft, Appendix 117, and is distributed thence to the connecting rods and cylinders. It may be mentioned that thea ilway serve a dual purpose by forming strengthening webs to the crank chamber. By the system thusi off separate pipes is dispensed with, and all the attendant dangers of interrupted lubrication through to leakage of a pipe or loosening off union nuts are entirely avoided. Fig. 81. Special attention should be drawn to the fact that notwithstanding their market accessibility. All thwarking parts off the engine except the flywheel are enclosed in oil-tight, dust-excluding cases. Green, engine S-Air made in two sizes, 35, 5060, developing the sepower at 1,300 and 1,250 revolutions per minute respectively. The weights are 152 and 246 ibs, respectively, completely equipped foreigning but without the flywheel. The cylinder dimensions are 105x 120 and I40x 146 mm, respectively. In addition, an 8 how to build an aeroplane and 80-100 pengenace manufactured which has 8 cylinders, did V formation. The feature off the Singanesses their remarkable reliability and ability off-running. Mr. Moore Brabazon FIG. 82. Used a 50-60, green, engine on his circular mile flight, which won 1,000 Daily Mail Prize in 28 October 1909. A 35H pengenace fitted Toth Army dirigible baby, while the new military dirigible is fitted with an 80,100 EP green motor. Printed by Nail & Co., Limited, Edinburgh. Green's British-built aerial engine, Green's patent aerial engine, represents years of labor devoted to the designing and construction of an engine which, while reduced to the closest possible limit in weight, shall be absolutely efficient under the varying conditions encountered in aerial navigation. Every detail has had the most minute attention. The weight this being scientifically reduced, without any cutting down off-bearing surfaces or wearing parts. The highest efficiencies maintained at all speeds, and during continuous running under full load. Green's engine has been adopted by HMY Office and was used in the successful trial for the 1,000 Daily Mai Prize. Green's Motor Patent Syndicate, Lid. 55 Berners Street, London, W. Makers 4, Patentees the Astor Engineering Company, Limited, J. Bond Co., Limited. 97 New Oxford Street, London, W.C. Inventors. Model makers' inventions developed and carried out under strict secrecy. Aero inventions as specialty sockets, lugs, brackets, wire strainers, bamboo, spruce, ash, cane, magnesium tubing, sheet aluminium, and all materials appertaining to aeronautics kept in stock or matatorter type no. Biplane cambered aerofoils, monoplanetail with vertical vanes. Price complete, cording to finish from 15. If built collapsible, price from 17. Types NOS. 2 and 3, double-ribbed aerofoils, double-surfaced with waterproof fabric front control, price from 25 and 65 respectively. May be had with detachable ends main plane set 3 and 7 extra. Aeroplanes type No. 20 horsepower biplane, front elevator, lever control, complete with British rotary engine, detachable ends top lanes. Price, according to finish, from 25 type No to 30 horsepower with rotary engine, 420340, 4 passenger. 555 aeroplane fittings, wheels, fabric, wire strainers, engines, propellers, and all accessories. Monoplanes 4.6, 7.6, and 12.6. Biplanes 7.6, 21, 33, 77, and 1,212. All British made. Parcels off materials for building from up to 15.6. Models Fine Art Aeroplane Catalog, 2nd edition, with our working drawing for building a model biplane, 4D. Post-free. The Twining Aeroplane Co. offices and workshops. 29B Grosvenor Road, Hanwell, Middlesex. T.W. K. Clark Go. Aeronautical Engineers Crown Works, High Street, Kingston-on-Thames. Gliders from 40. Aeroplanes complete from 38.0. Speciality, built-up Clark propellers, exact scale models, OFL standard machines. Contractors to HM Government, all model Mackin requisites. Send for lists. Telegrams, flyers, Kingston-on-Thames. Telephone 1183 P.O. Kingston. 100 IP Clark, propeller hearts, proofed aero fabrics for balloons, airships, gas bags, aeroplanes, gliders, and models from IOS. The square yard in weight. Waterproof, airproof, gas-tight, light in weight, moderate in price, in any color. Contain no rubber, made in England, various materials. These original materials have stood the severest tests for waterproofness and gas-tightness. Andone has been selected for Usain the construction of the great naval dirigible. Write for samples and information to Hearts, 21 Liverpool Street, London. E.g. telegraphic address, Crankcases, London. Relief Ahoy, and 4879 Central Large Small INF Udger 5T Hardened Foral Trades. Hami NF Uft Ecent Hardened, a Foral Trades, WW Mi VG, a VG off the pick and Eller of Rankle, Uminium. C. Acer CSFS2 I9 R Coswell Road, Affle. IXMRTS IF CRL Ondam, e.g. also iron cylinders repaired. On War Office and Admiralty, Lis 1 The Aeronautical Journal, edited 4th Council off. Aeronautical Society of Great Britain by T.O.B. Hubbard and H. Ledeboer, an illustrated quarterly devoted to the science of dynamic flight analysis branch's annual subscription. 6 post free. The Aeronautical Society, off Great Britain 53 Victoria Street, Westminster, London. SW. Telephone 3656 Victoria. Books on aeronautics, airships, past and present, together with chapters on use of balloons in connection with meteorology, photography, and the carrier pigeon. By A. Hildebrandt, captain and instructor in Prussian Balloon Corps. Translated by W. H. Story, 8 vo. Cloth 361 pp. 222 illustrations 350 net contents. Early history off art. Invention off the air balloon. Montgolfiers, Charlie Ayres, and Rosie Ayres. Theory off balloon. Development off dirigible balloon. History off dirigible balloon 1862-1872. Dirigible balloons from 1883-1897, 1898-1906. Flying machines, kites, parachutes. Development of military ballooning, ballooning in Franco-Prussian War. Modern organization of military ballooning in France, Germany, England, and Russia. Military ballooning in other countries. Balloon construction and preparation off gas. Instruments, ballooning assas sport, scientific ballooning. Balloon photography. Photographic outfit for balloon work. Interpretation of photographs. Hectography by means of kites and rockets. Carrier pigeons for balloons. Balloon law. Aerial Flight, Vol. 1, Aerodynamics, by F.W. Lanchester, 8 vo. Cloth 438 pp. Illustrate 6.00 net contents. Fluid resistance and its associated phenomena, viscosity and skin friction. The hydrodynamics of analytical theory, wing form and motion in parity. The aeroplane, the normal plane. The inclined aeroplane, the economics of flight. The aerofoil. On propulsion, the screw propeller and power expended in flight. Experimental aerodynamics. Glossary appendices. Aerial flight. Vol. Roman 2, Aerodynamics. By F.W. Lanchester, 8 vo. Cloth 433 pp. 208 illustrations 6.00 net contents. Free flight, general principles and phenomena. The Fugoid theory. The equations off flight path. The Fugoid 1852-1872. Dirigible balloons from 18,831,897, 1898-1906. Flying machine theory, the flight path plotted. Elementary deductions from the Fugoid theory. Stability off, flight path, as affected by resistance and moment of inertia. Experimental evidence and verification off the Fugoid theory. Lateral and directional stability, review of chapters Ito Roman 7, and general conclusions. Soaring. Experimental. Aerodynamics, aerial navigation. A practical handbook on the construction of dirigible balloons, aerostats, aeroplanes and aeromotors by Frederick Walker. 2nd edition, thoroughly revised and enlarged. 12 mo, cloth 175 pp, 128 illustrations 2.00 net contents. Laws of flight, aerostatics, aerodynamics, aeroplanes in practice, motive power. Screw propulsion for aeroplanes and airships, airships and dirigible aerostats, construction, aeroplanes and airships in use, supplement describing distinctive successful types. How to Design an Aeroplane by Herbert Chatley. 16 mo, boards 109 pp, illustrated Van Nostrand's Science Series, 50 cents contents, the aeroplane, air pressure, weight, propellers and motors, balancing, construction, difficulties, future developments, cost, other flying, machines, gyroplane and ornithopter. D. Van Nostrand Company, page 138. Knowledge is the ultimate tool for survival. By subscribing to Century Audiobooks, you help us bring thousands of years of human ingenuity back into the light. Check out the next manual in this series to keep building. Stay curious, stay prepared.